Good morning, everyone. This is the last day of the conference. The first talk of the day, it's online. Daryl, can you hear me?
Yes.
Hi, thank you very much. Daryl Holm will give the first talk of today. You can start whenever you are ready. Thank you very much.
Okay, I'll start as soon as I can. Okay, so. Turned out this is not the one I wanted. Okay, this is my backwards version of the slides. Okay, so I'm going to talk now. Is anybody going to introduce me?
Yes, we cannot see your slides if you are sharing. I'm not sure, but we can hear you and we can see you.
Okay, so you see me?
Yes, but not the slides.
So. Okay.
Okay. If you want, you can send us the presentation so we can share it for you. Okay, we can see your whole screen. We can see figures and folders.
Okay, this will just be a second. Okay.
Yeah, okay,
so
excellent.
How many people? Where's Steve? Is Steve there?
Yes.
He's here. Yes.
Great. Happy birthday, Steve.
Thank you.
I'm very happy to be giving this talk. So one of the reasons I'm so happy about it is that I've just received a whole bunch of more information from my student who is making movies for these emergent singular solutions of nonlinear wave equations. Let me begin. I'm going to discuss these emergent singular solutions. I'm going to begin by just reviewing a little bit about asymptotic expansions of shallow water waves, because this is, it's kind of a surprising thing. And then I'll derive a system of equations, which are a system of equations for KdV, which is written in the frame of a Burger's wave. Okay, the Burger's wave is a wave that makes a shock, and KdV is an equation whose waves make solitary waves. And then maybe I think we should just look at this for a while, and then after a while maybe I'll talk about integrable systems and other equations which have emergent singularities. So let me just get to the point of showing you what emergent singularities look like. So let's begin with looking at the asymptotic expansions that create shallow water waves. So the expansion is in two small numbers, which are ordered this way. And the thing which is very remarkable about this expansion is that as you add each successive order 1, order epsilon 1, order epsilon 2, as you're adding these, what you see is that each one of them is completely integrable. If you look at this one, this is the just the traveling wave, okay? And you can think of the eta as the height above the mean, so that's the wave height. And okay, we can have no trouble solving this equation. This is just moving to the right with speed 1. Okay, this is what I'm calling the Berger's equation. It has the hydrodynamic nonlinearity in it. These coefficients come from the expansion of the Euler's equation in a vertical plane with a free surface. So this one is if we can just move in the frame of this equation, the first one, and this is just a time derivative in that frame. And then this is the equation with the nonlinearity that produces a verticality in finite time, called the Berger's equation. Berger's equation has also some viscosity in it, and we're going to look at it when the limit of the viscosity is very small. Okay, so now if we move in the frame of the traveling wave, so and then in the frame of the Berger's wave relative to the traveling wave, and then we move into the then look at the next term in the asymptotic expansion. Then what we have this composition of maps, one simple, one nonlinear, and one dispersive. And so what's happening is that now we're looking at the Korteweg-de Vries equation, okay, but it's this is another famous equation, but this one here, the linearity, the dispersion term, regularizes the nonlinearity, which is trying to produce verticality, and so this is the famous story. Now, because it makes solitons when they balance. The thing which is interesting also is that in the next order, if you add this term, that term is actually, again, another integrable system. If you add these two terms, then this ratio is exactly 1. This is another completely integrable system when this one is ignored. Okay, that we've ignored this one and just look at the second one here. This one here is completely integrable. This has soliton solutions. And these solutions are especially interesting, and I'll talk about them later. But if we ignore that one and ignore this one, then this is again another completely integrable perturbations of the Korteweg-de Vries equation. Okay, so and it turns out that we can shift these coefficients, and there are 3 sets of coefficients here, and Yuji Kodama introduced a non-local way of changing the transforming the variables in a way that allows you to shift these to what's called the normal form. And the normal form is how you pick up the integrable systems. Okay, so the Berger's KdV system, how do you make KdV evolve in the frame of the Berger's wave? Okay, so now that's what the point of this part of the talk is what if you have a KdV solution that's just going, traveling wave is just going along in a trivial way, just making a constant speed. And if you add the Berger's kinetic energy into the Lagrangian for the system, and you look at the equation for this is you think of this as a Legendre transform, okay, but you do a Legendre transform to get the equation for the KdV, but in the frame of the Berger's, see, okay, so you did now. So what you're doing is you're putting the Burger's equation into the problem, and you're putting the KdV into the problem in the frame of the evolution of the Burger's equation. So you get a system. Okay, so the equations are for phi x, you call it v. Okay, phi is the velocity potential. So v and u is the Burger's velocity. And if you ask, for these equations that you get from the Hamilton's principle, they are Hamiltonian equations with a Poisson bracket that looks like this. It's not a symplectic Poisson bracket. It's a Poisson bracket, which is very interesting. This much here is just being carried along in the frame. But this one here is part of the transformation coming from this guy. Okay, this is what moves you into the frame. So you've written the Hamiltonian, it's variational derivative with respect to u. U is the velocity of the Burger's wave. This will be the Burger's wave here. But now this one here will be acting on this one, and that's going to give you a system. That's this system here. And multiplying on the bottom, this operator, you get this one. So you see, the full system is coupled. Okay, so if you start with no u, and v starts running, then v creates u. So that's how the system works. Okay, but so what happens? This was an amazing thing. We decided just to have the idea is what happens when the Bohr runs into a KdV shallow water wave. So if we just start with the square wave for the Burger's equation, and we run it into a soliton for KdV, what happens is that the front of the Burger's solution, the shock, accelerates the soliton. So the soliton is green, the Burger's is black, and it accelerates the soliton. But what happens is that that's not a surprise. But what happens is that the soliton height increases until it is actually higher than the Burger's, and walks away with it from it and starts propagating away from the Burger's shock, and it tore off part of the Burger's. See, there's part of the Burger's solution is inside the propagating along with the soliton. Okay, so is this really happening? Okay, we have the Burger's a Bohr has run into a wave and pushed the wave ahead of it in a way that is propagating, but it's now a compound wave. Okay, so let's look at this case here where the square wave of the Burger's wave is going to run into three little solitons, right? So you can think of this as the wolf and the three pigs. And this along comes the wolf is going to eat the pigs. But what's happening is that the soliton is increasing, and they're increasing fast enough that as the Bohr comes through, it accelerates the soliton. Soliton runs away. Bohr runs into the next one. It's getting away too. And Bohr runs into the third one. Okay, and now so what's happening is that this needs more study. This definitely needs more study. So let me show you some videos of what's going on. Okay, so this is actually a picture of what we just saw. So this is at the end. You see three, so this is space and this is time. So we have a wave moving from left to right. It means from in the positive slope. What's happening is that at first the one wave was emitted, then the other wave was emitted, and so this is what the velocity profile of the burgers looks like. Because burgers, this part has been captured by the KdV part. The KdV part has a trailing set of a wave train, but it also it has these compound waves which are moving away from it. Okay, so what else can I show you? Mm, I need to find these things now. Guess this be it? No. Okay. So uh this is a picture we've just seen. Uh okay. So yeah, okay, good. So this is the video of that of the one we've just talked about. And we can just watch this waltz happen. You see, this was what's happening. Okay, the three compound waves were created. So how did that happen? Uh, so what looks like what happens, you see that out here in the front, there's nothing in the U variable. It's zero. Okay, there's a square wave that's approaching. It has positive velocity and it's approaching. This is U, this is V, and these are little soliton shapes. They're set squared is what they're called. And as it moves in, so what's happening is that in communicating with this wave, it's now set up three profiles of the burgers, which have now they have three inflection points. Inflection points are in the profile are a signal. I think this is part of the creation of these compound waves. So, and the wave is accelerated by the front. It gets higher than the front. This is some kind of singularity, probably. And but it's restored by having part of the bore got enclosed in the KdV part of the wave. Okay, and so you can see that at each time you have these negative inflection points. We have creation if the timing is right. Okay, so if the timing is wrong, then here's two of them, and these are separated differently. And what happens is that as the Burgers wave propagates, this is what you expect to see, there's a ramp and the cliff in the Burgers wave. It first of all is developing this little bump with a negative, with a velocity going to the left, and the other one has velocity to the right. That velocity to the right is going to be captured by the KdV solution or not. Depends on the timing. Okay, so if we look at this, the Bohr made it past. And this is what you usually see in this is that when you look at a picture of a Bohr running over waves, you see that the waves are on the backside of the board. But if the timing is right, it says that this guy can be accelerated into a velocity which is higher than the velocity of the Bohr and move away and take away part of the Bohr with it. Okay. I find this absolutely amazing. I'm telling you about it because it's absolutely new. These pictures came in last night at a quarter till midnight, and I had already gone to bed because I had to get up early. Uh, and, and so I've been looking at them this morning, and I thought I would ask the question, do we think these compound waves are solitons in the sense that when they collide, uh, they simply exchange their momentum and they keep their identity. So let me show you this one here. Here are three compound waves. These are, we know what the formulas are for a traveling wave. We can solve the problem for that much. And so these move according to their height. So this one's going to catch up to this one and then this one. Okay. Then okay, so this is what we're looking at. Okay, so let's just watch what happens in the collision. Okay. So here's the first collision. Is it going to destroy itself? No, actually, these are very, very stable waves. And in the end, what happens is we have a train of waves which are ordered by their speed. And this is exactly what happens with KdV, but now we have KdV interacting with Burgers, and KdV that's interacting with Burgers is creating the compound waves, which look like soliton waves. Okay. So this is an absolutely new thing, and I don't know exactly what to do with it. But I thought I'd tell it to you because it's interesting. I'll let me go back to my talk. Let's see. So you can ask questions along the as we go if you want.
So, Daryl, there is a question. So
Yeah, good.
okay.
Let's hear it. What is the question?
Hi, on that space-time plot that you have behind you, or
Yeah.
on the screen, on the KdV part, is there a gap in between those three red lines going off? Are they really two red fronts with a little dip between them? And is the Burgers being trapped in the middle?
Yeah, okay. So here's what's happening. In the beginning, we have oh, okay. In the beginning, we have nothing. In the so sorry. If we look carefully, can you see? You can see the outlines of the three solitons here. There's one right at the beginning of the Burgers. Okay, and what happens is that during this period here, there's an interaction which tears off part of the Burgers. And there's a tiny little change in the slope here, okay, when it's running into the second one. Okay, so this one here is KdV, It's sitting there, and the Burgers is accelerating it, uh, and and as it and at some later time, then as the Burgers accelerates it, it is also creating a wave pattern that's following behind. Okay, this is the KDV wave train going back that way. And we're looking in the frame of the motion of the front of the Burgers front. Okay, so these guys go backwards and these guys go forwards. Uh, and and what you have is that this is the creation period here, creation period of this guy. And so the Burgers are being torn off here and being carried along by constant velocity. And here, compound waves are being created and propagating away at constant velocity. I don't know who you are, but you're probably as interested as I am about this stuff. You know, that's this is very, very interesting. This is a new system. And this system may actually turn out to be completely integrable.
One other question is about the square wave, because the one you're showing right now has a rounded front, but in the later simulation, it really had a sharp square wave front. Does that make a difference?
Oh yeah, well, yeah, because the difference it makes is that the ramp doesn't meet all the way to the cliff during the time of the collision, and it you know so like we know it doesn't always create a compound wave. Okay, but if we don't have the ramp interacting with the cliff, then we have more control of what the cliff is doing. So we just start with a square wave, which is wider. Okay. So we're these the ones at the bottom here. Okay, so three solitons. Oh yeah, okay. So what do we? This one's high, this one's low. So this is the ramp coming up here. And so the answer, maybe the answer to the question is that uh just with a wider wave, uh when we don't have the ramp running into the cliff, there's a different kind of interaction that's more maybe it's more
It was actually
stable.
the corner at the very front of the square wave I was referring to. And that
Oh, I
particular
see.
one, it's a little curved, and then later simulations it was sharp.
Yeah, okay. I think let's go to full screen. Uh let's see. Yeah. Okay, you're talking about this right here, right?
No, bottom.
So
At the bottom.
at the bottom.
Yeah, look at the leading edge of the square wave at the KDV. It's rounded right there at the corner, at the bottom, as it intersects the KDV.
Oh, that's right. That's right. It is rounded. Yeah. It is rounded, right. Now I understand what you're talking about. Yeah, and so this is zero. Oops. This is has Burgers is zero, and then it comes up smoothly to vertical, nearly vertical, and then rounded. So it's a rounded square wave. They can think of it as a difference between a hyperbolic tangent and another hyperbolic tangent in the other direction. And the width of it is determined, is very, very thin. So that's what the roundedness is. It means in that roundedness, I guess, is a thing that has enough time to interact with the soliton wave and shoot it up the front. You can see here it's shooting up, right? Okay, thanks a lot for your question. So that's, yeah,
Daryl?
go ahead.
Yes,
Yeah.
you can continue. You have approximately 20 minutes left.
Okay. My feeling about this was that people would be interested in seeing a new puzzle, and they could think about it. Everyone can think about it because this is an easy thing to do, and it's also on the archive. And so if you have an idea, just send me an email, and let's talk about it. Okay, so this is one of the questions is this an emergent singularity? Okay, is this the numerics stopping things that should be actually forming a shock? I mean, not a peak, like, and so what we're plotting here is the velocities of the KDB wave and the Burgers wave, but but the total momentum between them, the sum of their momentum, which is not a linear sum, because it's like u plus 1/2 v squared, but it's shooting up. Okay, this momentum is shooting up. So maybe there's some issue about a singularity in the momentum. Okay, if we're talking about analysis. Okay, so singularity can form in other equations. You can start out with something smooth, and just the nonlinearity can form singularities. Here you see an equation called CH, and what it can do is it can form a two basically, and you start. This is a waterfall plot where you just lift up one step for each time step. And if you start with a Gaussian in this for this equation, what happens is that, like the Burgers, it has the same it has the same nonlinearity that's coming from the Burgers. It leans to the right, it increases its height. But what's happening is that it develops this inflection point and that inflection point, one with a positive slope and one with a negative slope. They both rise. And as they rise, when they meet, they form a jump in the velocity. Okay, so it's an interesting type of singularity where two inflection points, one positive, one negative, meet, and they cause a jump in the derivative of the velocity here. Okay, and then this propagates away. But when it propagates away, it leaves behind another situation with an inflection point with a negative slope and one with a positive slope, and it makes it again and again and again until it uses up all this area, and it just makes this wave train of singular solutions whose momentum is a delta function. So what you're seeing here is the smoothing convolution integral. The shape is an e to the minus absolute value x that is on either side of this symmetric solution. These are periodic, and this equation is completely integrable. Even though it's forming these singularities, it's completely integrable, and you can see it having these elastic collisions, whereas it was one collides, this one here catches up to this one, and as it catches up, it gives this momentum to it, and the one in front ends up, just accepting the momentum from the one that ran into it. And that's it's pretty easy concept here, because you can actually make these, drop these equations into a form of a dynamical system that I'll show you. Okay, so the equation we just saw a moment ago is in this class called the B equations. And in the one we saw a moment ago, B was equal to 2. Okay, and so in the case of B equals 2, then this equation can be written as a Burgers-like equation being driven by a pressure, his gradient of this pressure, which is the smoothing of the solution. But if you ask for the solution of M, it turns out that the solution can be written as a sum over delta functions with amplitudes that depend on time only, and positions that depend on time only, and a velocity, okay, which is, of course, it's the convolution with the delta functions. These are the velocities. So you get a system which is not quite a Hamiltonian system unless B is equal to 2. But it is a system of in which the equation for this PDE has been converted into a sum of ODEs with this Hamiltonian here that has in it the convolution kernel. This convolution kernel here is the convolution. It's this e to the minus absolute value x is the Green's function for the Helmholtz operator, and the relationship between the momentum and the velocity is the Helmholtz operator. Okay, so they're only canonically Hamiltonian for the case when B equals 2. Now B equals 2 is the CH equation, and it has all these remarkable, interesting properties. But there are many of these. It turns out this, as a function of B, this equation has even more interesting properties. Okay, so if B is greater than 1, then starting with a Gaussian gives you just solitons moving to the right, and the shape of the soliton is this e to the minus absolute value x, which is the Green's function for the operator that is taking you from velocity to momentum. If you're between -1, if B is between -1 and 1, then you get ramps and cliffs, just like the Burgers equation. And if B is less than -1, then the waves move to the left, and they actually go out and stop, and their asymptotic shape is set squared. Okay, so set squared is always it's always the solution for nonlinear solitary waves, in this class of the quadratic nonlinearity. Okay, so if we start with Picon, and you have where you have a given value of P, a B, it'll, when it's in this middle formulation, it'll lean to the right and try to make a ramp and cliff. But if at a certain point you just change B from B equals 0 to B equals -2, it turns around and goes back left and goes into these asymptotic stationary states. And here's a profile of them. Okay, so the B equation is very interesting. And it has this property that it will if B is greater than 1, it will produce these picons, these solitons with the peak. And the problem is completely integrable only in 2 cases, when B is equal to 2 and B equal to 3. Okay, so here's our evolutionary equation written in more dimensions. So this is an equation which allows you to even have singularities in 2 dimensions and 3 dimensions, and the singularities form like on embeddings. Okay, so the singularities are actually embeddings that are carried by the rest of the flow. So what's happening in the case of in this case here actually is that you can think about the real line is uh, is undergoing a transformation and is carrying along these points on the real line. And the points are made visible by this convolution with this Green's function. Okay, so yeah, and so this is how the momentum looks in Rn, and this is how the velocity looks in Rn, and the rest goes through. You get equations which are, if B is 2, then you get these Hamiltonian equations. And when B is not 2, then you get a much more complicated system. And now this is in higher dimensions. And it's one point about B equals being 2 is that this motion, when that one's gone, this motion is in fact these are, of course, they're canonical Hamiltonian equations, but they're equations for geodesic motion on a space of n vector valued. Some n is the top of the capital N here. Vector valued surfaces embedded in little Rn, and with this cometric is the Green's function. Okay, that is relating the velocity to the momentum. Okay, so the theorem is, in fact, that this is a Poisson map, and this Poisson map is actually a momentum map. So a momentum map is a map from the phase space to the dual of a Lie algebra. And the phase space here is P and Q. Okay, so this is on some manifold with points Q and some cotangent bundle, fibers, called P, and this is the map from the P's and Q's to this is the dual of a vector field is one form density. Okay, and so think of velocity as a vector field that transports, that produces transport, and its dual in L2 is the one form density. Okay, so that's why this works. This works because you started out with a Hamiltonian system, and you've introduced this it turns out the Hamiltonian system for the momentum supports delta functions as a solution, and has solutions in space of generalized functions. And in the special case, when B equals 2, you can write this as a Hamiltonian system, and otherwise you could just use this momentum map. Okay, so how much time do I have left?
Approximately 10 minutes.
Oh, okay, good. Okay, so the way this motion occurs is the usual motion equation for fluid dynamics is that has a momentum map to the fluid momentum, which is this is the action on the right, from the right, but takes you from the phase space, for in this case, the phase space of or cotangent bundle of embeddings in Rn. If this will transport a momentum. This will transport momentum in fixed space, and the left action. This is right action. Left action on this cotangent bundle. Well, what it does, it's like the difference between left and right action for rigid body. You have a spatial angular momentum and you have a body angular momentum. And the picons are moving, or these singularities are moving as a result of the points in the domain are moving that are carrying those embeddings around. And the other one is the embeddings are moving through the points through the domain. So on the right, the embeddings move through the domain, and on the left, the domain moves the embeddings. And this is an interesting it's called a dual pair of momentum maps. So there's some interesting mathematics underlying these singular solutions of non-local partial differential equations. Okay, so let's see. So we have these two different actions, and the singular solutions of B equals 2 are just symplectic, and everything is, these are pretty these are pretty ordinary. They describe just how you, this one, if you action from the right, it's describing how you go from Lagrangian coordinates to Eulerian coordinates, and action on the left. So this is going from the Lagrangian representation of fluid dynamics to the Eulerian representation of fluid dynamics. So Q's are Lagrangian positions in momentum, and P grad Q, or PDQ, that just sets you up for symplectic dynamics, right? Because the differential of PDQ is the symplectic form. But this map from the phase space to the momentum densities is the map from the cotangent bundle of the Lagrangian representation to the Eulerian representation of fluid dynamics. And the other action coming from that's from the action from the left, it's the thing that produces these singular solutions. Okay, so this momentum map is, the gradient is replaced by this delta function, which is moving the space in which the embeddings are. And this is called a convective representation, but this is exactly the representation of nonlinear elasticity. Okay, so that the space is moving and it's moving the lattice. Okay, if you think of in elasticity, you think of the lattice as being embedded in the space, and then when you push on it, the space deforms and carries the lattice. So these are these two representations of material motion. Okay. All right. So this was the fun part, right? We saw this shape, okay, for the case of the Green's function of the Helmholtz operator. But you can go from, this one has an exponential shape, but you can actually go to any shape that you like, any shape that has a Fourier transform and is even, and the reflections, and so symmetric under reflections will give you a finite momentum, and it'll also give you this type of behavior. For example, if you had little triangles, okay, so with a no compact support, then you would also get this type of thing. We would just have different interactions because this would be a Green's function in the Hamiltonian, which is just linear and then changes slope. Okay, and this would be, you can also involve a Green's function and with compact support with a parabola, right? See what I mean? It's just exchanging momentum. So this is each one of these is a geodesic motion, and the shape of the prometric is exactly the shape of the solitary wave. Okay. When these guys interact, with one coming from the right and one coming from the left, then what happens is that a verticality forms. But just as the verticality forms, the amplitude goes to 0, and these things bounce. Okay, so this is not, yeah, it's a and this non-locality allows you to actually survive verticality. Okay, here's how it looks if you collide triangles. Now, these could be, and it turned out that these are not real singularities either. They also collapse to 0. But if you look at the parabola, these are real singularities. As these get closer, this guy gets higher and higher. So it's a bit, it's a bit like we were looking at before, but there is a singularity that can form from these types of collisions. If you start with a parabola as complex of compact support with triangles on either side, as it evolves, it'll form a whole variety of singularities. I think I'll stop there and have some more questions. Okay.
Thank you very much, Daryl. Let's thank the speaker. Is there any really fast question? If not, thank you, Daryl, once again.
Okay, my pleasure. Happy birthday, Steve.
Thank you very much.
I'll stop sharing.
Yes, thank you. We will have the break now. It will be approximately 20 minutes. Right, okay. so we can continue now. The next speaker is Francisco Montoya. Whenever you are ready, you can start, Fran.
First of all, thank you very much for the opportunity to present my work, and happy birthday, Steven. Today, I would like to talk to you about a particle that is moving around a black hole. It's a classical problem. But first of all, the interest about black holes now is growing, because now the black holes are objects that we can see in one way or other. And here we have the famous image. And well, in the black hole we have different regions that are important. In the center of everything is the singularity that generates all the issues. We have other important place, the event horizon. No particle can escape from the event horizon. A little bit outside, we have the photon sphere, where the photons are just moving around. A little bit outside, we have the innermost unstable periodic orbit that is going to play a very important role in our discussion. And we have a little bit outside the innermost stable periodic orbit that is also important, and well, more things moving around. Other interesting thing about black holes is that the black holes are rotating. For this reason, we have this region, this plane, where the particles are concentrated at moving around. And perpendicular to this plane is the axis of the rotation of the black hole. Okay. The equations of motion of one particle moving around a rotating black hole are those. Well, come from this Hamiltonian, and we need to calculate the derivatives. And a remarkable property of this system is that we have 4 integrals of motion: the Hamiltonian itself, the energy, the angular momentum, and the Carter constant. Okay. If we rearrange the equations of motion, it's possible to get a very simple equation for the radial coordinate, and is very similar to have an effective potential, and we have an effective energy, that is this thing. And you can see here some plots of the effective potential as a function of the angular momentum of the particle. Here we have the maximum, and here we have the minimum. And well, if we have a maximum, we know that there is a unstable stationary point here, and then we can construct an IM. We just need to do something very, very simple, and we can get also the stable and unstable manifolds. And well, I don't need to explain much things here, because I am sure that you are more than experts on these things. But the stable manifold is the set of trajectories that converge to the stationary point. And if we change the direction of time, we are going to have the unstable manifold. Okay. Well, first we consider the case where the black hole is not rotating, then we have spherical symmetry. And if we change the initial angle in the sphere, we have a different periodic orbit. Then, if we take all the orbits together, we can construct a three-sphere. And if we consider the same, but for the stable and unstable manifold, we have a spherical cylinder. Okay? That's very simple. And now the question is, what happens when we consider the case for A bigger than 0? That means that the black hole is rotating. There is a general theorem about NIMs. And well, one of the most important results is here by Fenichel that tell us that the NIMs are robust under perturbations. And also you can find a very, very detailed explanation in the book by Stephen and more results about it in the book. But for me, it was a surprise that also the perturbed system, I mean the case where A is bigger than 0, we can construct also a equation, a radial equation like this with one effective potential that is a little bit more complicated, but not much. And here we have some plots. And also we have here a maximum and minimum. Then we can proceed as before and say we can construct the NIM and also use the same argument. Of course, in this case, it's not is a deformed sphere in one sense or other. And to visualize the NIM and the invariant manifolds, we can use Lagrangian descriptors. Here there are some literature about Lagrangian descriptors. And thank you very much for all your explanations about Lagrangian descriptors, because I don't need to explain anymore. And here we have some plots. We consider initial conditions in the plane R-PR. And here we can see the red dot here. This is the intersection of the initial conditions with the NIM. And the stable and unstable manifold form a closed loop. And it's a trapped region here in yellow. And the other points here in very dark blue are points that go to the internal region and finish in the event horizon, and other points here in green. And if we increase the value of the rotation of the black hole, we can see that the trapped region grows and grows and grows. In one sense, the rotation of the black hole drags more space-time, and then the effect of trapping is bigger. And here we have the same, but for a different value of the energy. Here we don't have a trapped region. Then we increase the value of the rotation of the black hole, and then a little trapped region appears. And here we have the NIM in the red dot. And we can see that the trapped region grows and grows. Okay. Do you have any question? Very, very simple. Well, our conclusions are, well, the system is integrable, and we can construct a NIM and the invariant manifolds. we can easily visualize the phase space of the system using Lagrangian descriptors. This is something new, and it helps a lot to understand what is going on without the help of very complicated analytical calculations. This is an integrable problem. Then it's possible to get some expressions that are very, very large and, well, not easy to analyze. And as a result from our plots, we can see the effect of the rotation of the black hole in the trapped region. It grows. And thank you very much.
Thank you, Fran. Are there any questions?
Yes.
How does the rotation of the black hole grow? What's the mechanism for producing that?
It's very simple. The start, most of the black holes come from one star that is rotating. And to form a start, we need gas. And the gas, well, imagine that is in one place, and also is rotating. Is the product of the collision and interactions between different masses, and the collisions are not collinear. That's all. Yeah.
More questions? If not, let's thank the speaker again. Okay. Okay, we can continue with Mencia Reborido. You can start. Thank you very much.
Thank you. Good morning, everyone. I'm Mencia Reborido. Thank you so much for having me here today. It's been a pleasure. I come from the University Politécnica de Catalunya, and today I'm going to speak about the cavity flow problem. More specifically, the attempt that I have done at trying to find some possible overlooked branches of the bifurcation diagram for this problem. First of all, I would like to introduce the well-known cavity flow problem. It basically describes the flow of a fluid that is enclosed in a cavity. It could be a square or a rectangle. And we will focus on the two-dimensional version of this problem. One of the things that this problem has is the boundary conditions. Basically, what we have is we set the lids of the cavity to be moving at a constant speed. We can set either 1, 2, or however many lids to be moving as we want. In this case, we focus on the four-sided version of this problem, which means that which means that we will move every single lid of the cavity in such a way that is described right there with a constant speed. This problem is used as a numerical benchmark for validating Navier-Stokes equation solvers, and also as a test bed for several physical effects, as they display very important phenomena for the fluid mechanics field of study. As we can see, it is very intuitive that these boundary conditions will have the steady state solutions have shear flows near wall boundary layers and vortices. I have plotted right here some of the steady state solutions for different Reynolds numbers. Right here you can see the various phenomena that are displayed. And now we move on to the constitutive equations. We will have the Navier-Stokes equations in the stream function form. It will be defined on the square minus 1, 1. And obviously, for the Reynolds numbers, we have to define a characteristic length and speed and velocity for this problem. And it is very intuitive that we will choose the length to be the length of the side of the cavity, and the speed will be the prescribed speed for the lids of the cavity. Now we have the boundary conditions using the stream functions. And obviously, since we know the relation between the stream function and the velocity, we set it like that. It's a Neumann-Dirichlet boundary conditions. And one of the problems that we encounter when defining these boundary conditions are that this velocity profile will not be continuous in the corners of the cavity. This means that we will have the so-called corner singularities, and this causes to display very complex dynamics near the corners of the cavity. And also, we could have troubles when trying to numerically approximate the steady-state solutions or the solutions to the Navier-Stokes equation. There are several ways to mitigate those corner singularities. Some studies choose to not treat them and just treat the unregularized version of this problem. But we choose to mitigate this by prescribing another slightly modified velocity profile that makes the velocity all continuous throughout the lids. In this case, we use a double exponential velocity profile that sets the velocity at the corners to be 0, and the characteristic velocity is reached at the midpoint of the lid. And now in this velocity profile, we introduce another parameter given by k0, which basically represents the rate of change from the maximum point of the velocity profile to 0, so this slope right here. Obviously, for bigger values of the rate of the k0, we will have a more accurate model, but also it will be more expensive numerically. So we have to compromise and try to find the optimum value for that k0. And in this study right here that was done by my supervisors, they decided to choose k0 depending on how consistent the results from the bifurcation diagram start to get. So this plot right here shows some results from the bifurcation diagram, and you see it starts to be aligned from 10 on. And another very important property that this problem has is that due to the boundary conditions, we say that both the Navier-Stokes equation and the boundary conditions are D2 equivariant. That means that the stream function being under rotation and reflection symmetries displayed right there have this simple relation. And also, the fact that the boundary conditions are defined like that will cause that most steady-state solutions to be invariant under reflection and rotation actions. It could be either one of them or both of them. Now, moving on to the numerical approach that we have chose to implement for this, for the construction of the bifurcation diagram, we start with the discretization of the Navier-Stokes equation in the steady case. So basically, for the discretization, we chose to implement pseudospectral methods, which basically provide exponential convergence for our steady-state solutions, and also for the points used to discretize the Navier-Stokes equation, we chose a Chebyshev mesh, which basically the main advantage of this is that it clutters the nodes on the corners, which basically will help capture the complex dynamics that happens there. And on the other hand, to compute the equilibrium branches, we use a pseudo arc length continuation algorithm coupled with a Newton Philop solvers to solve the Newton-like iterations that we will have in that method. And we have a shift inverse transform applied to the eigenvalue problem to make computations easier. Okay, so now to construct the plot of the bifurcation diagram. As I have said before, the symmetries are very important in the steady-state solutions, so it makes sense to essentially try to classify the solutions depending on their symmetries. So basically, we define two parameters, which are S and psi Z, which basically means that if S is 0, the solution will be rotationally invariant, whereas if psi Z is 0, it will be perfectionally invariant. It's kind of like a way to measure how symmetric the solutions are. And we will plot the bifurcation diagram in this space right here, with the bifurcation parameter being the Reynolds number. And also, as I have said in the first slide, I have tried to find overlooked branches of the bifurcation diagram, and for this I chose to implement an homotomy method, which basically what I do is I perturb the system in order to try to land on some other overlooked bifurcation branches. In this case, basically the underlying idea is that by perturbing the system, the branching points will be lost, so everything will be shifted, and there's a high probability that we will find something new. But first, I will describe essentially what is the bifurcation diagram of the unperturbed system, the original one. As you can see right here, the solutions that are enclosed in the S = 0 plane are rotationally invariant, whereas if they're on the horizontal plane, they're reflectionally invariant. And there are some pitchfork bifurcations going on, and even some asymmetric, fully asymmetric flow in this branch right here. Also, there will be 3 hop bifurcations and 2 fold bifurcations that you can see right here, and also with the stability analysis and everything. The perturbations that I have chosen to implement have to do with the boundary conditions. Essentially, I chose to perturb the velocity by a small perturbation in the lids of the cavity. I chose to do this for 3 cases, where I just perturb the upper lid of the cavity, then the upper and the bottom, and then the upper and the right lid of the cavity. And with this, I break some symmetries of the boundary conditions, so there will be likely some changes to the bifurcation diagram. And this first case is where I just perturb the upper lid of the cavity, and with this, I break all the symmetries of the boundary conditions, and the bifurcation diagram, it ends up looking like this, with solution families going all over the place, like gaining and breaking all symmetries. And the most important thing that I'd say I found for this exploration are the isolated loops that you can find right here in the small region of the bifurcation diagram. They correspond to closed loops corresponding to smaller values of the perturbation parameter that I have chosen. For example, you can see this projection of the loops right here that correspond to different values of the perturbation parameter that I chose to implement. And one interesting thing is that if I plot the S symmetry value for different perturbation parameters, we get like a parabola-like curve that can resemble a fold bifurcation. I don't know if you guys can see it. It's kind of like a parabola right here. And by implementing a polynomial fitting of order 2 to this, we found that there's a fold bifurcation at this value of the perturbation parameter. Now moving on, I now broke the reflection symmetry by just perturbing the upper and the bottom lid. So the rotational symmetry for the boundary conditions is conserved, whereas the reflection symmetry is not conserved. And as you can see right here, there's a big family of solutions that is plotted in blue that stay in the S = 0 plane. It doesn't leave, it doesn't break symmetries. This means that solutions that are invariant rotationally, they tend to be that way. And also, as we had seen before, the pitchfork bifurcations were lost in the last bifurcation diagram, but in this case, we still have some pitchfork bifurcations that essentially have to do with breaking the reflection symmetry. And for this case, we also find a closed isolated loop, this one right here, that encloses both positive and negative values of the S symmetry parameter. We can see a close-up, a projection of this loop. In this case, we just found one instead of various loops. And for the last case, we perturbed the upper and the right lid of the cavity, which basically conserves the reflection symmetry but breaks the rotation symmetry. And contrary to the last bifurcation diagram, we just have everything all over the place again. So for example, solutions that are invariant reflectionally, they don't really tend to stay invariant reflectionally through the, for example, you can see right here, it starts enclosed in the horizontal plane, and then it moves to the s equals 0, and it goes kind of all over the place. And in this case, we also found another loop right there that is kind of like the last loop but rotated. And you can see another projection of this. So to conclude, the main, I did not obviously find any new bifurcation branches, but we still came out with interesting ideas. Firstly, I want to highlight that we tried to find as much accurate numerical methods as possible, because as we have seen, small perturbations in the system can cause very different results. And on the other case, we can see a prevalence of rotation over reflection actions. This means that, for example, when we conserve the rotation symmetry, we can see that solutions that are rotationally invariant tend to stay that way, whereas it doesn't happen for the reflection symmetry. And lastly, as we have seen with the newfound fold bifurcation, there could be some explorations done on the value of the boundary perturbation none. And those are my main references, and this is all for today. Thank you very much.
Thank you very much. Are there any questions? If not, let's thank the speaker again.
Thank you.
All right, we can continue with the next speaker that comes from the best department in Spain. Victor Villaragut, you can start.
Thank you very much, and thank you very much for having me here today. This is a joint work with Ana Maria Sanz from the University of Valladolid. Let me introduce what nickel solid systems are. We will start by telling you how they emerged. They were models written by Gurney that mimic the behavior of the Australian sheep blowflies. And well, we're gonna consider actually systems whose components represent patches of these flies, and they have some migrations from one to the other. And our goal is to find sufficient conditions to ensure the existence of global attractors. Okay. Well, first, I will tell you about these systems. Let's say we have a patch I, and x sub I of t represents a population at patch I at time t. And it will vary with respect to birth. Birth is a nonlinear term, and it also has a delay, which represents the time that it takes to go from conception to birth, actually. We also will take into account mortality, which is linear with respect to the population, and emigration from one patch to another. It is also linear with respect to the population on the origin patch, and of course immigration from the other patches to the one we're considering. It's also linear. Since both, these two addends depend linearly with respect to the population, we will put them together and we will combine them in a decrement in general with respect to the population in the patch. So with this system of equations, we can already impose some hypotheses so that we can give some results on the existence of global attractors. First, we will assume that all the coefficients are almost periodic. We could go with recurrent coefficients. The proofs will be the same, but this is the case mostly studied in the literature, and is the one that raises more interest. So we've chosen to do this case. Actually, all the coefficients are positive. The decrement and birth control, which birth control is this, maybe here. This C here, which makes birth go down as time goes to infinity. Okay, they're strongly positive, and there is no migration between patch and itself. I mean, migration goes outward or inward, but no, there's no self-migration. Okay, we will set up a setting of a skew product semiflow so that we can deal with this nonlinear, non-autonomous problem. Okay. First, we will define the hull of the coefficients, which is a closure for the compact open topology of the time translate of the coefficients. This is a compact set because we chose almost periodic coefficients. And we can define a flow by translation, by time translation. Okay? This is a minimal flow in the sense that all the trajectories are dense. And with a little trick of notation, we can consider this family of Nicholson systems. There is a different system for each omega here. And if the funny part here is that if we take omega equal to the original coefficients, we recover the original equation. But actually, we have a whole family of systems which makes it a lot easier to study the behavior of the solutions than to study a single equation, okay, as we will see. Well, we will consider the phase space, the usual phase space for these finite delay equations, which is a Banach space with a supremum norm, and we will define this local skew product semiflow. The first component of this semiflow is just the base flow we defined on the previous slide, and the second component is the solution to the corresponding to the corresponding equation to that omega. Okay, so well, this Banach space is strongly ordered if we consider the component-wise order, and we can find a positively invariant subset, which is the base, the base or the hull times the positive cone. Okay, this is positively invariant, and the solutions are defined globally there. Okay, for the semiflow. Okay, so well, this is just here for the sake of completeness. A global attractor is a with respect to a family of subsets of the phase space. It's an invariant and compact set which attracts forward in time the elements of that family. Okay, so we can prove that there exists a global attractor in the positive cone with respect to bounded sets. Okay. This is the first result. Not the most interesting one that we were going to prove, but we have this result here. Actually, we assume uniform persistence at 0, meaning that initial data which are strongly positive at 0, finally, in the end up surpassing any lower positive phase bound. Okay, then we can prove that well, this can be checked numerically with this, as we will see also later. And then we can prove that there exists, if we assume this, a global attractor in the interior of the positive cone. So the points in the attractor are strongly positive functions. Okay, and this is with respect to compact sets. Okay, and we have a final theoretical result which says this. If we assume uniform persistence at 0, and we assume that this condition is satisfied, this condition is on the coefficients, only on the coefficients, so it's easily checked. And it's a little bit better than the ones in the previous literature, so we can recover in more cases. Then there is a unique, almost periodic solution that attracts all other solutions at an exponential rate, that is exponentially fast. Okay, so let's go on to some numerical simulations. We will consider a Kronecker flow, which is a finite dimensional case of the base flow that we saw before, okay, on the two torus. And this is a minimal flow. And we can consider this two-dimensional quasi-periodic Nicholson system. Here, well, the coefficients are chosen so that conditions are satisfied. I mean, And the two patches represent two patches amongst which there is a flow of population. Okay. So it's a little bit more applicable than the ones before. So here are the condition, the numeric condition that we saw in the last theorem would say that the continuous lines, one color for each component, should be below the dashed lines. Okay, that's the condition we have imposed. And in the same three examples, these are three different examples. Okay, the second best condition there is, which is the one previous to the one we just found, says that the continuous lines should be between the green lines. These were given by Teresa Faria. Okay. So we have gained some applicability. Also, if we consider pullback attractors are more or less the same thing, but the attraction with respect to the family of sets, of subsets of the phase space is in the pullback sense. Okay. Then we can try and visualize the global attractors with these pullback attractors. We will see how in a minute. Just taking into account that actually the global attractor is a copy of the base flow. That is the image of continuous function for the compact open topology from the two torus into the interior of the positive cone. Okay. With this in mind, well, we cannot represent a function over each point of the torus, but we can evaluate them at 0, which is the outstanding point in all the half line, left half of the real line. Okay, and we can approximate in the pullback sense like this, starting from a strongly positive initial condition. We can approximate that value, taking a limit, and fixing a grid on the two torus, a uniform grid. We can have an image of the global attractor for these systems. Well, finally and very fast, we can change the rate of migration between the patches, and this is just a numerical research. And the global attractors in different examples vary monotonically. Okay, and we can also change the mortality rate in one of the in the second patch. Okay, and the global attractors increase monotonically. There are no intersections, which there might be. Well, that's all. Thank you very much.
Thank you very much, Victor. Are there any questions? Yes, there are.
Thank you so much. That was a very interesting approach to a biology problem. I'm curious why this fly is being studied. Is it just interesting mathematically, or is there like a need in Australia to know more about its behavior?
Well, as far as I'm concerned, it is only interesting mathematically.
Fantastic.
So I don't know. Well,
okay.
I don't think it has.
That's
any
a
more.
worthy reason. That's fantastic. Thank you.
Yeah.
More questions? If not, let's thank the speaker once again. All right, we can continue with the next speaker. The next speaker is Igor Belik. You can start whenever you are ready. Thank you very much.
All right, thank you so much. Well, and thanks to Victor, we have a little bit more time. So I'm supposed to end at 12, and I'm happily take this extra few minutes to talk a little bit more about the details of this work. But first of all, I would like to thank the organizers for making this conference happen. And well, and happy birthday, Steve. And then I was a really big fan of your work and of your books. And as I told you, so your book, the introductory book to dynamical systems, it was the first dynamical systems book in English that I read, being the undergraduate students in the Leonid Shilnikov's group back in the early 90s. And well, the talk I'm going. What? All right, so is it better? I'm trying to handle this oofs. There is a way to go back with this? Okay. Okay, do you have the pointer or something? Well, I'm tall enough. I'm good. So maybe that's better. All right. So the title of this talk is very similar to Steve's books on homoclinic bifurcations and chaos and analytical methods. Well, mine is slightly different with the small caveat. Then we will deal with piecewise smooth systems. So, well, this is the work with my collaborators, Vladimir Belik, who is my father, who turned 81 this year, but he's still research active and a former PhD student. I have, funding, different aspects of this work is funded by NSF. And also, since ONR is the sponsor of this conference, I'm also happy to mention that I have the active ONR project, where we use the ideas inspired by Steve's work to understand the laser dynamics with application to beam, high energy beam combining. Well, the main thing here is the following. That, well, I don't know what to hit here. Just the excellent. All right. Well, first of all, let me. Here in this conference, we've seen nice talks about the Lagrangian descriptors and many other things. But in this talk, I would like to go to fundamentals, to where it all started, and then where Steve made the major contribution, which is the chaos theory and the Lorentz attractor. So, and the global bifurcations. And let me start with this talk with a somewhat provocative question. Does the Lorentz attractor exist? Well, we discussed it. We've seen this, the use of Lorentz system. Recently, in a few talks. But this question was answered in the affirmative only quite recently. Well, in 1999, by through the computer-assisted proof by Warwick Tucker. But the problem here with all the systems in the continuous time, so the ordinary differential equations, is that basically because the systems are non-integrable, we don't have the solutions, and then we can understand the dynamics of the systems by constructing geometric Poincare maps, but they are not explicitly linked to the flow of the system, because we don't have the solutions. And in this talk, I'll show you that we can go around this obstacle by designing the piecewise systems, basically gluing systems out of linear systems for which we know the solutions, and we can do everything explicitly, so without assistance or any computer assistance. Well, that talk has two parts. So, well, we will first of all discuss the existence of the Lorentz attractor, and then we will characterize all the bifurcations in the piecewise smooth analog of the system. And then we'll also look at the non-classical homoclinic bifurcations in the piecewise smooth systems. And it turns out that this area is completely underdeveloped, while we understand the global dynamics in continuous flows very well, or relatively well. Well, now when it comes to non-smooth dynamics, well, our knowledge of the bifurcations and other things and stability very often fails. Well, we have a paper, the recent review paper with Rachel Kuski, David Simpson, and Maurizio Porfiri-Chaos, which reviews the state of the art in the global bifurcations in piece-smooth systems over the last 20 years. So I would invite you to read this one if you are interested in this subject. But going back to the motivation. So rigorous computer-free proofs of the existence and bifurcations in chaotic systems are rare or almost non-existent. Obstacles to such proofs include the absence of exact solutions, and I'll convince you that the piecewise smooth systems, well, they can give us the way to go around this. So, and the system that we built here is the piecewise smooth analog of the Lorentz system. So, well, we're all familiar with the structure of the Lorentz system, which has the double, the butterfly. Here, what we do the following. So we partition the phase space in X, Y, and Z into 3 parts, and then each part of the phase space is described by those 3 systems. When we have the saddle, and we have 2 stable foci. Well, right here, well, basically the phase space is separated into 3 pieces. So we have this box here where the dynamics is described by the saddle system, and then outside of this region, the dynamics is described by the corresponding systems for the focus dynamics. Well, these points here are stable. However, they can be they're stable in the subsystems, but they can become unstable. They can become saddle foci in the full system when we consider the whole dynamics. Again, the system AR here is defined in the phase space, which is separated by this half plane, which goes is sort of Z-shaped plane here, and then its left counterpart is described somewhere here. So, basically constructing those systems, so it might be a little bit technical, but basically doing this, we are sort of doing the school project. We start with the shoebox, colored wired, and glue. So the shoebox here, basically, it's this region, the saddle region here, and then we write the normal forms for each of the equilibrium point, and then we sort of connect the wires by glue. It requires some finesse, but it's constructing such systems, but it's fairly straightforward geometrical approach. Well, what we get out of this is the following. This is the analog to the classical Lorentz system. Well, this is our glued system. This is the Lorentz system, and it shares all its properties. It has the symmetries, it has the equilibrium of the saddle and foci. Well, the global section here, Z equals B, is the analog of the global cross-section in the Lorentz system, which is rho, or R minus 1. And then the parameter B here, well, this one, it plays a role of R minus 1 in the Lorentz system. And the saddle value is set to be positive, so it really serves as the very straightforward analog of the Lorentz system. All right, so what we can do here is the following. So this is part 1 of the talk, the short talk, when we can set the parameters. And again, the system is glued of the linear system. We have we know all the trajectories. We know pretty much everything about the system. So, and then we can write the parameter region in which that system has no sliding motion inside the attractor. What it means is that when it comes to the piecewise smooth systems, there are always switching manifolds. Like in this case, well, those manifolds here, they separate the flow of the red and the blue trajectories. So it's the half plane which extends up. And then it's possible that a trajectory here, for instance, the unstable manifold, can land on this pink area. This pink area is a stable sliding motion, so creating all these headaches. But one can design the parameters, and then if B, well, again, B is an analog of R minus 1 in the Lorentz system, is lower this value, then, well, these trajectories never land on this pink area, and then they all land on this global Poincaré section, the green one, such that, well, the sliding motion doesn't play any role. And then we are basically we are going to the complete analog of the smooth Lorentz system under this condition. So, and if it is so that we can easily well, do many things. For instance, this is the example of the homoclinic butterfly construction. And again, well, when this trajectory goes all the way to here, well, here it forms the trajectory going all the way down, creating this homoclinic butterfly. But look, what we're able to do here, we're able to give the explicit value of the parameter that corresponds to the homoclinic bifurcation, which is out of reach for the real model. So the typical results there of the existence types, like they exist a parameter, but here everything can be done explicitly. Well, how it's done? Well, we obviously need to construct a Poincaré map. But again, it's a straightforward exercise, because we have the linear systems. So the Poincaré map here, it's the mapping of this Poincaré global cross-section, the blue one, into itself. It requires writing the model for the mapping T sub 1 from this cross-section to the lateral side. Well, T1 and then T2 going back. Well, this is the tedious but straightforward process, because the equations, well, the trajectories are known to us, so it's linear solutions. And then we end up at this mapping, which is discontinuous because okay. Well, the mapping is discontinuous because this separating region here, which is the part of the stable manifold of the saddle, well, it maps into the saddle, and then, well, it needs to be determined whether we're landing on the left or on the right, corresponding to this discontinuity. But anyway, this is the two-dimensional map, which is the analog of the known two-dimensional Lorentz map, well, derived with many work, particularly by John Guggenheimer, but those are geometrical methods because they are sort of inspired by the flow. This is the explicit one. Well, because it's a linear system. And then what's the interesting thing here is that, well, because the G, or excuse me, it says X and Y, this is the X direction, this is the Y direction. Well, the Y component here is contracting, and Y is not present in the X equation, such that we end up at this one-dimensional master map. So for X, where, well, X bar indicates the next iterate, it's X of n plus 1. We've seen in a few talks, well, I think Eric Bolt mentioned the standard Lorentz map for Z, which has this cusp. This is for the X variable. So that's why it has two branches here, and then there is a way to explicitly describe the transition from the stable dynamics to the chaotic map. Well, this trench attractor exists, and then the interesting thing here, well, it's a 1D map which is amenable to almost cobwebbing analysis. And that could be summarized in the theorem, which is, well, basically gives all this famous, well, transition from the stable dynamics to the homoclinic butterfly as B increases, then the formation of the heteroclinic bifurcation, when this, it's exactly as in the Lorentz system, when the unstable manifold of the saddle lands on the stable manifold of the saddle cycles. Well, I don't give you all the details, it's exactly as in the Lorentz system. Well, but notice that we have everything explicit in the parameters here. Well, this is the region for the existence of the Lorentz attractor, but plus, because it's a linear system, we even can calculate the Lyapunov exponents explicitly. So, showing that all the trajectories inside are of saddle type. Well, this is, and then, well, when B increases, this parameter, which is analog of the R, which is a Reynolds number, we have the conditions when the attractor this becomes a quasi-periodic attractor here, which is somewhat similar to the so-called foliation condition in the smooth analog of the Lorentz system. This suggests, well, the illustration of this. Well, when B increases, we have all these points. It's all explicit, so there is no computer analysis here. This is the trajectories showing what's happening here step by step. Well, with this particular case, when corresponding to the emergence of the Lorentz attractor, when the unstable manifold here lands on the stable manifolds of the saddle cycles, well, leading to the emergence of the Lorentz attractor, it has this slight weird shape because of the discontinuity. So those boundaries here, they correspond to the switching surfaces that separate the phase space into three parts defined by different dynamical systems. And finally, the question here is what happens when the dynamics becomes more complex, when the trajectory lands on the sliding motion. The sliding motion is stable behavior. So it adds some stable parts to the trajectories, and then everything can be done explicitly. So here it goes beyond the Lorentz system. I'll be done in 2 minutes. So, and then what we've got here is that basically we have no sliding motion. We have this standard scenario as in the Lorentz attractor. When we have sliding motion, then because of the emergence of these little stable pieces and fragments, we have the stabilization, and then the chaotic attractor basically destroys, and then it becomes the stable orbits. This can be all classified through this extension of the Poincaré map by adding an extra piece, well, which is described by the Filipov's dynamics. But after all, we end up at this one-dimensional master map, which has some stable fragments. Well, those correspond to the super stable orbits. Well, those are familiar with the cobwebbing. Well, you probably recognize every time you have the flat fragment, you have stable orbits. And then as the result, here we'll get some non-classical homoclinic bifurcations, which is this is the classical homoclinic bifurcation happening in this system. When we have the homoclinic, and then the homoclinic, unstable homoclinic, gives birth to 2 saddle cycles. But once we have the sliding motion, what we have here, this is just before the bifurcation. This is the homoclinic orbit. This is a stable orbit here. Once we touch the sliding motion surface, what we actually have the following. The unstable homoclinic gives birth to the stable period 2 limit cycle. Well, of course, the saddle cycles need to appear to separate the stable points from this stable orbit, but this is completely unexpected behavior in the continuous time. And then through this, we can get the description of the Lorentz attractor destruction. All the details are in our recent papers. We have, well, 3 of recent papers published in Chaos. Just to conclude, this approach can be applied to most chaotic dynamical systems. We also applied it to saddle focus attractor. We construct a very similar system in a similar way. And then if you ever need the chaotic system for which you can construct the invariant measure, for which you can give the explicit analysis in terms of the parameters. You know all the solutions. We have such systems. One is this piecewise smooth Lorentz system, which allows for well the any data-driven analysis, or it can be used as a test bed for comparing well your method to the ground truth system. Well, and then finally, when it comes to the discontinuous dynamics, it just shows that those systems, they need more exploration, and then the global stability theory and the bifurcation theory is, well, still needs to be developed, because it can generate somewhat unexpected behavior. So with this, I'm happy to conclude. Thank you so much.
Thank you very much. Are there any questions? If not, let's thank the speaker again.
Thank you.
All right, so let me start by thanking the organizers for this kind invitation, where I can come and talk chemistry to mainly nonlinear dynamicists. Never an easy job, but when I try to tell nonlinear dynamics to my chemistry colleagues, that's an even harder job. But I'll try. I think this is a title that I think yesterday there was a whole bunch of talks, and Steve's group has been actively involved in looking at these kinds of systems. I'll try to give a motivation to what these things are, kind of get an overview of what we've been doing, trying to follow up, mainly motivated and inspired by the work that Steve's group has done over several years, including collaborations with Barry and Greg Ezra and so on and so forth. Harris yesterday mentioned his trajectory and timeline of intersecting with Steve's world line, and he started with the infamous meeting in Sagaro, Spain. And believe it or not, Harris, I was also present in that meeting. Okay, I was a postdoc with Greg Ezra at that time. I just joined. I think Greg was invited to this meeting to go, and Greg, being Greg, just decided not to go, and he told me, I'll fund your entire trip, why don't you go to Barcelona? That was my first visit to Spain, actually, right? Wonderful couple of weeks, actually. That's where I met Steve for the first time. I'm not sure if Steve remembers me, but we sat across from each other and I think had a cup of coffee or something. And Steve was interested, of course, because I was a postdoc with Greg and he wanted to know about what I'm working on and so on and so forth. Amazing thing is that that picture of Steve that I have from, 30 years ago, and I see Steve sitting in front of me, he's sort of remained invariant. I mean, I can't, it's more or less, it's just been there. So that was a wonderful meeting with Steve. And then what was interesting in that meeting also, I should mention, is that as a young chemist interested in nonlinear dynamics and sort of thinking, what are these people talking about, what are the stuff that, I might be interested in, to have this amazing opportunity at dinner time to sit on the same table with Vladimir Arnold and Jürgen Moser. Everybody else was a mathematician. I was the only chemist, theoretical chemist. And Arnold, as usual, was pretty talkative. And he kept asking people to introduce themselves. And everybody said, I'm working in this, I'm doing this theorem, I'm working on this problem. And then the turn came. And I was dreading, because what am I going to tell him? And Arnold was sitting right next to me. Moser was right opposite on this table. We already had emptied about 1.5 bottles of wine, so that might have, things might have mellowed down a bit. But when my turn came, I just sort of very softly said, I'm a theoretical chemist. And I still remember to this day Arnold just leaning over and says, "Good, keep us honest." That was his remark. Anyway, that was an amazing meeting. So that was my first meeting with Steve. And then, as it turns out, our world lines have crossed constantly. Many years after that, when I moved for a position and we were studying what are called the intramolecular vibrational energy redistribution problem, which is a notoriously difficult problem in chemistry, we were thinking of techniques of trying to understand how nonlinear resonances actually manifest in the system and how they shuttle or transport energy. And we were actually trying to look for ways to sort of analyze that in a very meaningful way. So, for example, we needed to actually know which resonances come at what time, because that was very important, because that actually told us which parts of the molecules were getting excited at different times. And we're sort of unsure exactly, and I sort of had this in mind. And then Steve's paper comes out on time frequency analysis, wavelet-based time frequency analysis, and that was exactly the tool we were actually looking for, and that was it. So my first PhD student used that, and we actually studied a molecule. With that, it gave us plenty of insight, and lo and behold, I get a long email from Steve saying that how there are many other ways you can look at it, and so on and so forth. So that was my second email contact, and then I actually ended up overlapping. So I was on a sabbatical in Germany, my first sabbatical. And then part of that sabbatical was actually spent in Bristol with Steve, where I actually overlapped with Holger at that time. And that was just punctuated earlier by this beautiful paper by Steve and Holger and with Andy, which was on the HCN-CNH isomerization that Holger briefly alluded to. It's one of the most beautiful papers I've read in JCP. It's a long paper. You need a lot of patience to read that paper. But it really made an impact. It was a beautiful analysis of that system. It still stands out. And so I ended up going to Bristol, overlapped with Holger, started discussing, and so on and so forth. Then I came back next year again in the summer, passing through, going to a conference to US, stopped in Bristol, talked to him, right? And this is how. And more recently, again, part of my second sabbatical, I was supposed to pass through Bristol, literally. I mean, it was for just about a couple of months, on my way to US, coming from Germany, and COVID hit, and I must say two things here. One was that it was a very uncertain time because all the flights were locked out. We didn't know how we will get back to our country. But this brought out the other aspect of Steve, which I'm truly grateful to, which is his magnanimity. And then I said, Steve, I don't know what I'm going to do because I was supposed to leave and I cannot leave and I have no idea. It's completely uncertain. And Steve says, don't worry, just stay. Stay as long as you need to be. And thank you for that, Steve, because that meant a lot. Because during those times of uncertainty, which I'm sure most of us felt in different ways, this was a very reassuring short email, but very reassuring because we couldn't see each other at that time. Macarena actually urged me to give my slides very quickly, so thank you for being very patient because I have been sort of, as you all, I've been on a very long trip. This is my fourth conference in this trip, between people talking on polaritons and chemistry and spectroscopy and another retirement, and now back to nonlinear dynamics. So it's big long thing. But one thing I couldn't put here was that when the COVID rules were relaxed, the Wiggins team at that time, Matthias, Macrina, Francesco, we all actually went to this park to have lunch, of course well separated, and I actually took a photograph. Unfortunately, I could include that photograph here, but if any of you, I'll show you that photograph where we have all of us sitting in this park, well separated. But anyway, so there have been, and this continues, it's wonderful, and hopefully I'll get to see you, our world lines will intersect further. And you would think with all the intersections, I would have written a paper with Steve, but that hasn't happened, unbelievably. But then I believe that collaborations are not really only about writing papers. I think this is sort of a common misconception people have. Collaborations also on a higher level happen when you have very meaningful interactions and when you actually get inspired to do something or get an idea. And in that sense, Steve's comments over the emails or when I met him, they have been very inspiring. So thank you, Steve. Right, so let's see how does it go. This big button supposed to be the next one. Yes, so there it is. Happy 650. So you see a collage of figures from this time. You know, I'm not sure how many of you will recognize this. I'm sure Steve certainly does. That's that paper that I told in 2004 JCP that Holger probably definitely remembers. Okay, a beautiful picture. This is more recent, Victor Macrina. So right, so and that actually is the picture from the time frequency analysis paper that he published on the water molecule, which was my postdoc work with Greg at that time. So time frequency analysis, transport in 3 degrees of freedom, Lagrangian descriptors more recently. These are all techniques that we've actually borrowed from Steve and have put it to hopefully good use in actually understanding chemical, molecular dynamics. I should put definitely a slide up for all the brave soldiers over the years who have hung out with me. You realize, as you will see from the research, I mean, we do classical dynamics, we do quantum dynamics, we do semi-classical dynamics. So everybody in my group are supposed to do all three. They cannot get away with just doing one. Okay, and this is difficult because whenever the students first come, they're chemistry majors. They are asked to go and take a course in nonlinear dynamics. Okay, they are asked to read parts of Steve's book or papers, and you know, it's pretty unsettling in the beginning, but then they come out actually at the other end, hopefully, and all of these guys made it. Okay, so and great job. So I'm very thankful to all these guys for being helpful, and of course there's a whole bunch of people which are listed over here who have been over the years given great insights. So let me start with the paradigm in chemistry. In chemistry, the paradigm is that of a transition state, a mechanism that is associated with it in going from left to right, basically separated by a barrier. Okay? These are reactants, those are products. That's sort of the standard paradigm. And transition state theory is an extremely powerful way of looking at calculating reaction rates here. There's lots of different notions here. There are, you know, talk about energy flow. There talk about, of course, behind that you have the invariant manifolds. There's intrinsic reaction coordinates. There's dividing surfaces. There's a lot of notations here. And notice here in one particular thing, in all the chemistry textbooks, you will see that this is just labeled as a reaction coordinate. Nobody explicitly ever says what that coordinate is. Actually, there's a good reason for it. And you don't know it, because if you specify what a reaction coordinate is, you've solved the dynamical problem. So that's pretty challenging. Now, this is the standard paradigm. Part of this paradigm, which chemists have believed in for nearly a century, is that whatever separates reactants from products is this particular object, which is called as an index 1 saddle. This is a saddle point. We have heard about it. And this is what chemists believe that pretty much controls everything. And you can actually write this neat transition state theory expression, and that continues to be used and will be used, you know, for a very, very long time. But the interesting part is that if you look at these multidimensional potential energy surfaces, that's not the only sort of saddle you have. You also have higher index saddles, for example, shown here in the context of a very interesting work that happened, let's say, about 5 or 6 years ago. So you have these higher rank saddles. For example, you can have 2 unstable directions. Okay, and the question is, are these higher rank saddles actually relevant for chemistry? If you ask most traditional chemists, they would say, nah, it's not useful. Really, this is it. Okay, this is the one that's useful. These guys are just a headache, essentially. Well, the question then, it turns out now people are realizing, after doing a lot of experimental and dynamical studies, they're realizing that that's probably not true. These higher rank saddles are going to play a very, very important role. Okay, so they're not just something that you can just wish away if you want. So that, of course, raises the question: what is the mechanism for such reactions if they're going to utilize these higher rank saddles? Now, one of the things that you know that a lot of people don't realize is that you can have, if you're studying reactions, I mean, theoretically or experimentally, it's quite possible that you might get similar rates, okay, but the mechanism might be quite different, right? In other words, you go from reactant to products, okay, on this multidimensional surface, right, there might be multiple pathways, Okay, these are different mechanisms. That's how you should think about it. Okay, but the rates might come out to be the same. So if you are just going to measure the rate and going to infer, okay, that null experiment actually doesn't tell you anything about whether different pathways were used. So this is something very important. It's also important from people trying to design control strategies. Okay, let's see how. Okay, good. So there is a huge literature now in terms of these dynamical effects and reactions, where higher rank saddles are probably becoming very important. Actually, it is very interesting, because if you go back, even to 1996, there's already a statement here that studies of dynamics of motion along this surface will be required to understand this reaction. You can clearly see the higher rank saddle over here. Okay, this is by Kendall Houck's paper. Then there is Schaefer's paper, where a lot of interesting things start happening. And in mechanochemistry, this is chemistry which is influenced by actually applying external forces. You can actually induce these new structures in the potential energy surfaces, which are going to now change the entire mechanism of the reaction. Okay, so this is not just theoretical. It's not in the theoretical realm anymore. I mean, there are actual experiments which had already hinted even 15, 20 years before. But now, with better experiments, you're actually getting to see them happen, and people are now beginning to ask this question. How do these high rank saddles play a role? That's just one aspect of it. And let's see if it works. Okay, so what I'm going to do now is going to talk about one part. So this talk has actually two stories, and hopefully I'll get to both the stories. So the first story is about this higher rank saddle, and this actually happened sort of when I was actually in Bristol. We were isolated, and Shiva Naik was a postdoc with Steve at that time. And then my student was sitting in India, and I was stuck in Bristol, and we were sort of doing certain things, and it suddenly occurred to us that there are these interesting problem that we can look at. Now, what this problem is, where high rank saddles are important, what this problem is this slide will go further. Go, yeah, okay. So there is this what are called double proton transfer reaction. So there are many molecules where you have two protons, one sitting here, for example, and one sitting there. And both of these protons are going to transfer eventually to the other side. Okay, they're called double proton transfer. So if you think of two hydrogen atoms moving from one side to the other side. And there was always this question that in these such double proton transfer reactions, do they happen stepwise or they become concerted? In other words, does one proton transfer first, then the next one, or both transfer go together? Okay. Now you might say, well, okay, why is that really important in chemistry? Okay, in chemistry this is important because if it's a stepwise transfer versus a concerted transfer, right, the mechanisms are different. And when the mechanisms are different, then when you try to think about how to modulate that chemistry in terms of either actually adding some new chemical groups or changing the coupling or driving the system, it becomes very, very important. Okay, so knowing that mechanism is very important, and it turns out that there are several work already done by this group. In fact, Fernandez Ramos, and a few years back, they started even earlier than that, where they were looking at sort of the quantum mechanics of such systems, and they were looking at effects of symmetry breaking and mode specificity. In other words, exciting different modes to see what's going to happen. So this was a good model to take. So we took this model. Now, let me give you a warning first. This molecule that they were considering and what experiments actually have worked with, it has 108 degrees of freedom. Okay, so very simply, the phase space is about, give or take 200 degrees of freedom. Okay, so right, so yeah, I mean, yeah, we can talk homoclinic orbits here. We can do all sorts of things, but this is high, very large dimensions. But the nice thing here is that first of all, there are two reaction coordinates, because remember there are two atoms which are moving, two protons that are moving. There are two reaction coordinates, and there are 106 transverse modes. Okay, and it turns out if you look at just the reaction coordinate alone, it's a double well sort of potential because it's symmetric transfer. Okay, in each direction, and you can construct these symmetric and antisymmetric combinations, and you can actually write just for that reaction coordinate this uncoupled mass scale Hamiltonian. Now, the question was that what do you do with the rest 106 modes? Okay. Now it turns out that these people who did the theoretical work and also evidence from experiments that you cannot neglect the transverse modes. In other words, there are some transfer modes of particular symmetry which couple very strongly to this Hamiltonian. In other words, they perturb this Hamiltonian very, very strongly. If you don't take them into account, then you cannot actually explain the experimental finding or spectra that they are measuring. Okay? So it turns out that they also very nicely told us which ones to take into account. Okay? So the minimal model, that is a model with just the the minimum amount of complexity that we can handle at the moment, is this. You take this uncoupled 2 degree of freedom thing. First you couple them with this sort of a coupling. Now you might say, why is that the leading order coupling? That actually just has to do with the symmetry of the system. So the symmetry demands that certain couplings cannot be allowed, okay, essentially. So it's only this particular symmetry, this coupling, say quadratic in excess and quadratic in antisymmetric. And then the third transverse mode, which actually couples in this particular way with a frequency of its own. Okay. Now, just so that for future reference, just to give you an idea, there are minima there, right? There were double well, there were reactant minima. The time scale, you should think of it as about 2 in these reduced units. And the at the transition state, there is this another minimum. So if you think about it, it's a hill, and then there's this transferred coordinate which is sitting on top of it. Okay, so that frequency, that time scale is about 5 roughly. So, but what is interesting about it is that in this particular model, that time scale here is actually independent of these coupling strengths between that third mode and the symmetric and antisymmetric mode. Okay. Now, so just to keep in mind. So what did we do? We said, well, okay, what we can do is we can look at this potential. By the way, this is a false image of this. It's not a 2-dimensional thing. It's a 3-dimensional thing. Just sort of, it's a cartoon, if you want, at this point of time. The Hamiltonian we have is actually a 3 degree of freedom Hamiltonian. Okay. So we actually take a whole bunch of initial conditions right at the top of this saddle. That's the second rank saddle now, second index saddle. We launch them, and they are just above this. This is classical dynamical study, so it's just above that. You know, it's just about 0.1, 1/10. Okay. It's a pretty small, but just above that. And just to give you an idea, the distance from this minimum to this second rank saddle in that same unit is about 2. So you know, it's a pretty small amount it's above. And we launch these trajectories, and what we do is we forward propagate to find whether it goes to the product, and we backward propagate the same trajectory to make sure that it goes to the reactant. So we are actually counting only the reactive trajectories. So if you do that, you take this ensemble and do the dynamics. And what we did was we actually looked at what is called as a concerted motion. That is, if you have a reactant and a product, then it doesn't visit these 2 other intermediates, and it just directly goes from the reactant to product. We call it concerted. On the other hand, if it starts over here, it actually visits one of these intermediates or both of the intermediates and get to the product, we call it stepwise. And essentially the question was, well, if you just look at what is happening to these dynamics of this initial ensemble, what is going to happen? Okay. So let's just look at this. Now, the question that we were going to ask was this, that this is a completely classical thing, so we're going to forget about tunneling, entanglement, coherence, and all that stuff. Okay. Now, this is the other thing that I should sort of mention at this stage, and you'll see it again later, little later in this talk, that in chemistry, nonlinear dynamics is obviously important because they are nonlinearly coupled. There's nonlinear dynamics. That's a classical part. But all chemists also believe that, of course, that molecules are quantum mechanical. Okay. So when you tell a spectroscopist that here's a nonlinear dynamics result, the first question always is, are they relevant quantum mechanically? And that's not an easy question to answer at all. Okay. Because the question is, of all the nonlinear dynamics insights that we're going to get, how much of it actually carries over when you quantize the system? Okay. But for now, I'm just going to neglect this. Okay. So the mechanism is, what is the mechanism? What is the role of this? And then there are many other questions one is asking. Again, in this picture, these are the intermediate. Okay. And this is the reactant, and that is the product. If you go straight across over the second rank saddle, that's concerted. And if you take stepwise thing, that's called stepwise. Okay. So we just wanted to know what is the fraction of this concerted to stepwise. Ah, it's slow. Okay. Hopefully it's not slide. Let me just try. Yeah, she's faster. Okay. So what we wanted to know was this fraction of concerted trajectories, okay, related to the total number. This fraction plotted versus coupling strength, okay, of the transverse mode, that is third degree of freedom, for let's say 2 different transverse mode frequencies, one low frequency and one sort of a moderately high frequency. And it turns out that there are, remember the transverse mode couples to both the symmetric and the antisymmetric modes, okay, they're both couplings. If you consider only the antisymmetric mode, what you find is that that fraction of concerted trajectories actually increases. If you consider only the symmetric mode coupling, it actually goes in the opposite direction. So whether the third mode, transverse mode, couples to the antisymmetric part of this reaction coordinate or the symmetric part of the reaction coordinate gives you completely opposite. So the first thing was, how do you intuitively understand this? Okay, it turns out you can actually take a pretty good guess at trying to intuitively understand this, and you can basically say, okay, look, I know the potential energy surface, what it looks like. So basically what's happening is that whether you strongly couple to that mode, the antisymmetric mode or the symmetric mode, actually has to do with the fact that the low frequency part will give you a large excursion when you're trying to cross that the second index saddle. So as you're coming across a saddle, if you have this very low frequency mode, it's a very shallow thing, right? So you will basically have a large excursion, and now you can get lost, and the concertedness will sort of go away, and it'll do a stepwise thing. So basically, what you would expect from this very intuitive sort of argument is that this sort of a gating that happens at the second rank saddle, that this fraction should be a monotonic function of the third mode frequency, the transverse frequency. Okay. Well, that's something one can actually immediately test numerically. This is the plot. So what we are plotting over here is this a particular coupling held fixed, the other coupling being varied. This is again the fraction of concerted trajectories, and here's the coupling just to remind you what it looks like. And this is for 3 different value of the frequency. Okay. So that's omega y. So 0.4, 0.2, and 0.3. And what you can clearly see that it is non-monotonic. Okay. So in other words, as you decrease the frequency, actually the 0.3 case comes down, and then the 0.2 case actually goes up. And whenever you have such non-monotonic behavior, you immediately realize that this simple intuitive picture is actually wrong, and dynamics is doing something very, very important. Okay. So in order to actually characterize this, which is very clear that the phase space is important, it turns out that even in the chemistry community, fairly influential papers were being written on this mechanism switching, okay, and people understanding this, and they come up with some sort of a ad hoc way to understand this. Okay, what they said was, look, what's happening? Both my protons can just go across, that's the concerted, or they can go one by one. Okay. But they said, look, really, experimentally, I cannot resolve very short times. So maybe, it is stepwise or it is concerted, but this stepwise time difference is so tiny that I would think of it as stepwise, concerted. Okay. So they came up with this idea. They had something called as a delay time definition. So basically, they were motivated by the fact that if you just looked at the prefactor of this typical transition state theory, it has some value at room temperature, and they said, okay, let's look at this time gap. In other words, just imagine you have a gap time between one hydrogen moving and the other hydrogen moving. Let's make a statistics of this. Let's look at this distribution, and this gap time, let's plot this out. Okay, and if this gap time with this as a cutoff, right, any fraction that's below that is dynamically concerted. In other words, this is something experiment can never resolve, whereas everything else onto this side is stepwise. Okay. So in other words, if the delay is too short, it's essentially concerted for all practical purposes. Now it turns out that this particular notion of gap time was actually put by Hauck and co-workers, used actually even earlier by people like Ahmed Zuhail and Jerome Burson. So it's been around in chemistry for quite some time in the context of these kinds of questions. But what is interesting is that Hauck writes, for example, that we note, however, that this timing border lies in arbitrary but reasonable boundaries. In other words, how do you put this cutoff, right? Where do you choose this? Why should even there be such a gap time, right? So our question, of course, immediately was, is there a dynamical foundation for this delay time distribution? Okay, where does this come from, and does it generalize to higher index saddles? So what we did was we said, okay, for the same system, we're going to do this. It's the same sort of thing. We'll start from the reactants. We end up at the products. And basically, we are going to start the clock whenever the trajectory enters this intermediate time, and stop the clock once it comes to the product. And you just look at this delta tau, that's the gap time, and just generate a distribution. And we'll choose a cutoff time which is around 5, which has to do with this unstable, the frequency up at the top of this second rank saddle. Just look at this distribution. And it turns out, well, actually, if you look at this, you can get something like what Hauck and all were doing. This is the gap time distribution for different transverse mode frequencies. And what you can see is that for very low frequencies of transverse mode, you can actually see this as a function of coupling. These distributions actually either are to the left of the cutoff or the right of the cutoff. But the most complicated part is this 0.3. In other words, remember I showed you the 0.4, 0.2, 0.3, 0.2, and there was non-monotonicity. If you look at the 0.3 case, there are coupling regimes where you see these clumps of gaps. In other words, there is this gap time comes in clumps. Okay, and that is pretty complicated and highly non-perturbative. You cannot use perturbative arguments to explain that at all. Okay, trust me, we tried and we failed miserably trying to do this stuff. So this is an extremely difficult dynamical regime that we are in, which is reflected in that earlier plot that I showed you. So that gap time actually is going to capture these complications. That's what it looked like. Okay. Now we said, all right, how are we going to? And here comes the plot and then the equation that you guys have seen for dozens of times already. And we said, well, this is a 3 degree of freedom system. We're not going to be able to look at Poincare surface of sections, but can we at least use this powerful tool of Lagrangian descriptors to see if the Lagrangian descriptors are going to pick up exactly this kind of complicated gap times. And what I show you, of course, I don't need to explain this to you at all. So what we did was we actually looked at this, we computed the Lagrangian descriptors, okay, and what I show below is the comparison of the gap times. Okay, so what you see in blue over here, they are basically concerted, that is the gap time is below the cutoff, and what you see over in green are stepwise. So these are gap times, they are to the right of the gap time, and you can see clear one-to-one correspondence between what is happening with the gap time and what the Lagrangian descriptors are actually showing us. Okay, so there are still a lot of other details that are missing. This paper was just a start to understand this higher degrees of freedom system and trying to see how far we could go with the Lagrangian descriptor. And right now there's a student in my lab, because this student's already graduated. He was trying to basically understand that complicated dynamical regime and what insights the Lagrangian descriptor will give. Okay, in the next few minutes that I have, let me wrap up by telling you the second story. Okay. Second story has to do with dynamic matching. We had Matthias talk about it yesterday, and there were other references to this. Well, it turns out that for those who work in this caldera in dynamic matching, they know that this was the paper that sort of started it all. This was a paper by Barry Carpenter way back in 1985, and he was looking at these four-fold branch points and implications for certain things in chemistry. It's called stereochemistry of the reactions. And there's also a lot of other influential works that have happened after that. We have done the dynamics and looked at dynamic matching, for example, and that's particularly from Dan Singleton's group. But my student was actually asking lots of questions about this, and she said that, has anybody gone back and studied that original model of Carpenter to see what's actually happening for dynamic matching? And I said, not that I know of. So I shot off a mail to Barry Carpenter and I said, hey Barry, has anybody studied the dynamic? Barry said, no, not really, I don't think so. And then he pointed out that there were some very nice special effects that he had pointed out in those papers, okay, which he said, I don't really understand it. So all right, we said, okay, good, and this was perfect because this was supposed to be a work that was going to happen for Barry Carpenter's special issue. So it made all the more sense to work on this problem. Okay, here, let me quickly show you now what this potential is of Barry Carpenter. This is the potential. Here's the four minima that you have here. Here is that caldera region over there, right? This is the plot coming from a different paper, but this is a similar thing. And this is all about, whether you go directly, do a dynamic matching, or you meander around here and go off and violate dynamic matching, okay? So this, let me show you the form of the potential. It's a little bit complicated. And I mean, I can talk, many people are interested, why Barry actually tried to come up with this kind of a model. Okay, there were reasons. But the important thing here is that this parameter f over here, that actually controls the depth of this caldera. So it's a flat region, but you can also make it depressed. Okay, you can make it sort of go slightly deeper and deeper and deeper. Okay, so that parameter f essentially controls this caldera. So what we were interested in, we said, okay, let's therefore look at the extent of dynamic matching as a function of this depth of this caldera. Okay, what is happening with that? So this is the results. What we do is we launch trajectories from one end coming from one of these transition states. Okay, and they are slightly above this transition state again, and they are for varying energies. So in black you see for 0.1, these are actual physical units that we were using, because that's what Barry was also using. Okay, and then you go sort of increasingly higher up above that saddle. Okay, and you launch these trajectories from there, and you ask how much dynamic matching happens, what fraction, as a function of the depth of this caldera now. Okay, and we actually saw something dynamically now which Barry had actually seen himself, which was that if you took, for example, if you look at, let's focus on this purple or the green, for example, you see that as you increase the depth of the caldera, the extent of dynamical matching actually goes up. It actually exhibits a maximum, and then there is a very slow fall off. Okay, so in other words, if you are at a particular energy, the caldera depth is fixed. You're launching these guys, right? And now that energy is kept fixed, but now you change this caldera depth. It seems like you make more and more dynamic matching, okay, and then if you make it deeper, you would think that, well, it should be more and more and more. No, it just turns around. It starts to slow down. That fraction goes down. That's a very non-trivial effect to see in the system. And basically, what it actually tells us from a dynamical point of view, that you cannot use statistical theories even for very deep calderas, and that is something that experimentalists have been observing now once they're reanalyzing all the data that they had probably interpreted according to Barry many years ago. So it turns out that, of course, you can take a phase space viewpoint. Here this is a 2-degree freedom system, so we could just look at it just to bring out for you how subtle this phenomena is. If you look at the caldera depth of 0.008 and in about twice that, if you compare the phase space, okay, a Poincare surface section of this, they pretty much look identical. Okay, you cannot pick them apart here. Okay, but if you look at the fraction of dynamic matching that happens at 0.008, which is somewhere over here, versus 0.017, where it is out there. Okay. So if you just look at the surface of section, it's actually pretty hard to just say that the dynamic matching should have increased by nearly an order of magnitude. Okay, so it's quite a subtle effect actually. And now we come back to this. I think people are talking about fate maps. I forget who it was. Somebody talked about fate maps. You did. Okay, here's the fate maps if you want, in some sense. So we go back and look at this fate maps for this different caldera depths. And of course, lo and behold, they are significantly different. And as you can imagine, if you were to actually compute the Lagrangian descriptor, of course, they would pick up these structures. There's without any doubt. And it turns out that these substantial differences that actually happen actually has to do with various classes of trajectories that exist for this case, which take you away from this ideal fraction, whereas they all sort of disappear over here, giving you a very large dynamic matching fraction. Okay, so I think one such trajectory was actually shown here. Trajectories can do sort of very interesting things. They can, for example, get completely thermalized and then escape, or they can actually avoid the caldera region entirely and go away. And so there's a very rich dynamics sitting over here. But as I said, remember, and let me end the talk with this. This is all good and well. This is all classical mechanics. I have not taught quantum mechanics at all. So the one question that my student posed to me, and she's a bright one actually, she said, hey, but how, are they quantum? What's quantum dynamic matching? I said, oh, that's a good question. I don't know what quantum dynamic matching is. None of these people who do even molecular dynamic simulation in chemistry worry about the quantumness of it. I said, well, does it happen? Does it occur? How do you even prove that all of this is going to hold in the quantum world? Okay. Well, we said, all right, we have the model, we know what to do, and well, okay, so let me skip. These are things that are very familiar to you. Okay. We said, does the quantum care? right? So classically, you're entering over here, you dynamically match, and this is a very subtle thing, a lot of parameters, dependence, non-trivial stuff. But okay, quantum, what happens in quantum mechanics? If I imagine quantum mechanically thinking about this, is there even a phenomenon called dynamic matching? That's the first question. Second, if that phenomenon exists, is it even close to what the classical mechanics is showing, or is it completely different? And remember, in quantum mechanics, you can have lots of different effects. You can have coherence, you can have entanglement, you can have tunneling, you can have above barrier reflection, so many things that can actually muck up this entire phenomenon. So we said, all right, let's study this. So we actually define certain regions which go with those different minima. Okay, we start a wave packet over here at A. Quantum mechanically, we actually propagate this wave packet. We compute the analogous what are called domain probabilities classically, right, as a function of time, and we say, okay, how do these things compare? Now remember, the caldera region is actually in purple. Okay, that's the region you want to focus on. Okay, so if you do the quantum dynamics, what do you see? Amazing. It just follows it. Okay, here's the result. So if you look at the case where you have dynamic matching, yeah, you will start over here. You can see that the classical mechanical results are solid lines, and you will see that the probability from the reactant region goes away. What grows up immediately is the caldera region. So that's the dynamic matching happening quantum mechanically, and goes away, and then the other probability starts to build. Now you might say, well, one probably got lucky because classically things are very higher. So one way to check that, of course, we know this from classical quantum correspondence, and having done my postdoc with Greg many years ago, is tune down the effective Planck constant and see if you get closer to the classical result. Okay, that's what we did. We basically took the Planck constant at 1, tuned it down by 1/10, and lo and behold, they're literally on top of each other. So we know that that's what we are saying. These interesting deviations you're seeing in the population in the caldera, those are quantum effects, and we're yet to understand them completely. Okay, so there's a lot of interesting stuff happening. But mechanistically, quantum mechanics is essentially doing the same thing that classical is doing, and that's wonderful. But of course, that's not the entire story. This is a very nice classical quantum correspondence. There are certain initial conditions where you avoid the caldera. There, the classical quantum correspondence, even when you reduce the Planck constant, is not great. And our understanding here is almost non-existent. So we don't really know what's happening over there. Okay, so the answer to this question I posed is that is dynamic matching happens quantum mechanically? Answer is yes. But on top of it, I should say that there are also quantum effects that can actually sort of modulate this in some interesting ways. And there's actually very little understanding of how that happens or what is the mechanism of that. So I'm almost done. That's my last slide. Just a few final thoughts. Okay. So you will see in the background, if you can see, there's 3 letters here, I, V, and R. That stands for intramolecular vibrational energy redistribution. Now, in both the cases that I've shown you, the caldera or the dynamic matching problem, as well as in this multiple index saddle problem, the part that has not been understood yet from a dynamical perspective clearly is how the energy flow is being modulated, or how it's playing a role in the mechanisms that we are observing, or switching of mechanisms that might be happening. There are so lots and lots of work that are already now recognizing that these things are very, very important, and a nonlinear dynamics plays an absolutely essential role in beginning to understand what is actually happening to these systems. So as I said, there are questions about quantum manifestations, and one of the things, of course, that chemists would like. Now, I went back. I think before the COVID happened, Barry was visiting Bristol. I had a long chat with Barry. It was a very interesting chat. And I asked him, I said, there are all these works in nonlinear dynamics, people talking about these manifolds and how they do this, all these insights we have. How do we take this over to the chemists, the guys who are running trajectories and stuff? But I said, Shrihari, that's a difficult thing. I've been trying for 4 years. This is not easy. So I said, what will it take? So we went back and we started discussing, why is transition state theory expression, the naive one, why is it so important? Because there's a recipe, okay? You need the information at the minimum at the reactant. You need at the transition state. Automated software does it for you now. Okay, you get this, you calculate partition function, you put it, you can compute the rate. It might be off by sometimes an order of magnitude, but hey, that's been a great sort of guiding line for a century. But okay, what would it take? The analogy would be, in my opinion, that whatever we are talking about, for example, higher index saddles or caldera, there has to be a way in which we can now start to express the rates explicitly in terms of properties of these invariant manifolds, some specific properties which are computable, which is something that one can compute and plug in, and they say, oh yes, indeed, this is much better. This is what is going to tell me exactly what's happening. Okay. Of course, there are many other things in that long discussion, but I'll be happy to discuss over lunch at this point of time. So, and I think this is also a sign of how chemists are beginning to realize that things are not that simple. This is actually a very nice statement by Dan Singleton in this paper at the end. He says, chemists tend to equate the rates and selectivities and isotope effects for reactions with the properties of transition states and implicitly assume that the product is fully defined by transition state geometry and interactions. When instead product selectivity depends on the details of trajectories on a dimensionally broad energy surface, the complexity of chemistry seems daunting. For example, it is disconcerting that after both experimentally and calculationally characterizing the transition state for this reaction, we still do not know the major initial reaction product. However, fully understanding the role of trajectories in complex reactions should prove an intriguing intellectual challenge for the future. By the way, future was not that far back. That's 2006. This is not a statement made in 1986 or 76. This is 2006, which means, and in fact, there is one more paper that just come out from Roald Hoffman's group and Hauck's group, just came out 3 months ago, where they actually talk about why dynamics is so essential that we need now in a whole class of reactions. So the understanding, the implications of dynamics are beginning to be appreciated in chemistry, and I'm sure the nonlinear dynamics as well. And so Steve, stick around. I think there's going to be a lot of interest in this as we proceed. So thank you very much for your time.
Thank you very much, Srihari. Are there any questions? Okay.
Thank you very much. That was really very interesting presentation. So first of all, forgive my ignorance. Can you, people that are doing experiments, can they experimentally measure the dynamic matching? Can they do that?
Yes,
okay.
Absolutely. Because they know what the products are, right? So they know which are the major minor products. So and one of the experiments that were performed were sort of the inspiration for Barry in '85 to actually write that paper, okay. Right? So it turns out that there are, I haven't shown a single molecule here. That's what all my chemist friends complain. They said, your talks don't have molecules in them. So these days I do put a odd molecule over there.
I do not complain.
Yeah. So it turns out there are molecules, they have lots of components to them, okay? So there are what is called a stereochemistry of the molecules, how a particular group sits relative to another group that sits there. And these are things that they can measure directly, so they know what's happening in the system. And so it turns out dynamic matching, for example, can influence very significantly the different stereoisomers that are formed. And so there is direct experimental measures for those.
Okay, thanks. And some follow-up question. In the last part, you showed that more or less the quantum mechanics model is following, in some sense, the classical model, which is also my general understanding. I have seen things like that in many cases. You compute periodic orbits in models, you compute eigenfunctions, and you see the maxima and the minima more or less following that. Right. The question is, experimentally, can the experiments also agree with what you show there? That have there been any experiments that show more or less similar behavior with what your model, classical model, is showing or not?
You mean in terms of quantum? Yeah. So that's the tricky part. I don't think we are there yet. So in other words, what most of the experimentalists do is they do their experiments, which is of course in the fully quantum realm, I would assume, right? That's the molecules don't know classical per se, but then when they try to interpret, they run trajectories, and they're happy if they see a qualitative sort of thing, right? So nobody has dug into the quantitative aspect. For example, the plot that I was showing right here, right? I mean, there is this very significant effect that can happen, right? So for example, over here, there's a significant difference in the extent to which the dynamic matching is happening over here. But that experimentally would require, for their reactions, it's impossible to do quantum dynamics on such large systems, right? Now, is there a if I understand your question, is there a direct experimental measure which would say that, hey, look, there is this thing? No, we're not there yet. And probably I think it's also our job to basically tell them what to measure. But that would precisely tell what this is.
Thank you so much.
Okay, I don't think we have time for more questions. It has to be really quick. Mateos, really, really.
I have one question. Initially, you showed that you have a difference of behavior if you change the depth of the caldera. But I saw in the Poincaré sections that you had that maybe you cannot see a big difference, but I saw two small islands in this one case. I'm sure that you cannot catch with Lagrangian descriptors very good this behavior, because there is an associated stable periodic orbit, and in order to do this, you must decrease the region of this space and to apply the Lagrangian descriptors, or to find the periodic orbit and to compute the invariant manifolds using the classical method.
Right, absolutely.
I'm sure that there is a transport that can affect the results. Even for
I mean, you know, I agree with you, but there's also some other things. So we looked into it. There are indications that these guys, the fact that they are not there is important. But actually, the dynamic matching orbits are the guys you're seeing here in blue. They are the dynamic matching orbits, actually. Okay, but they do have an influence. You're right. But we don't completely understand that. But I'm pretty sure there must be an effect like that.
Because there are many bifurcations there, and you can also have resonant bifurcations. Because if you describe 2 or 3 times the same family, you have also the generations of other families.
I mean, as I said,
if you analyze the phase space, because I have done many times this, it's interesting to study this.
I definitely completely agree with you. Definitely. But my purpose here to show this was that at a very cursory glance, if you just look at it, right, you wouldn't be. And that was the whole motivation, was to say that you have to dig deeper into the phase space to start learning exactly what's happening. But the other interesting point from the quantum mechanical point of view, which I would just mention very quickly, is that if you ask what is the size of the Planck constant, right, in this phase space, actually quantum mechanics cannot see these guys. I mean, the Planck constant size is much bigger than those guys. Okay, so it's going to just sort of average over it. Now the question is whether quantum also is going to exactly see this. So it turns out the big outstanding question is, how do you construct a dynamic matching fraction quantum mechanically? Remember, I didn't show you the analog of quantum mechanics for this guy. Turns out it's pretty damn hard to define that guy. It's not easy.
And also about the question of Harris, I want to add something that except the papers of Barry Campeter, there are very interesting papers about the experiments, about dynamical matching from Doubleday and Reyes. And also there is a good review paper that also Barry proposed me to read when I was in Bristol, from Doubleday for the caldera potential research. There are many papers that explain this.
Certainly.
Okay, let's thank the speaker again.
Can we remove this one?
This is for that, so you can.
Okay, I will not use it. I will just copy and. Yeah, sorry, ma'am.
You can copy it in the desktop.
Yeah, sure. Thank you.
Okay, we can move to the next speaker.
Yeah.
Yes, it's working. Raul Das, you can start. Thank you very much.
Today I am going to talk about nonlinear normal mode and how with an operator theoretic approach we can quantify it and investigate the impact of internal resonance and dissipation on the framework. So I will start with a brief introduction of normal modes. Like, what exactly are nonlinear normal modes? Basically, they are like the nonlinear extension of the idea of linear normal modes, which are essentially the eigen solutions of the linear systems. Now, there are fundamentally there are two different schools of thoughts to perceive the nonlinear normal modes. One is pioneered by Kauderer and Rosenberg in 1960s, where they focused on the functional relation between the degrees of freedom of the systems, and they illustrated that relation on the configuration space, which is x1, which I have shown it in figure 1, x1 and x2. So here the dotted line, the dashed line illustrates the linear relationships, it illustrates the linear normal modes of a system, and the curved line, we call them modal lines, they corresponds to the nonlinear normal modes. The same thing also perceived in a different way by Shaw and Peer in 1990s, where they focused on the topological structure of the solution space. They defined the nonlinear normal mode as some manifolds in the state space, which are invariant under the flow. As we can see, if we can look along the direction of x1 dot, we can project the manifold into x1 and x2, it will be exactly same. So before going in details of nonlinear normal mode, let's review what we call linear normal modes. Linear normal modes are basically the eigen solutions or the eigen subspaces of a linear systems, where the stable, unstable and center eigenspaces controls the dynamics of the entire phase space, and the invariant manifolds, they are tangent at those tangent to those invariant subspaces at equilibrium point. Now this is the spectral expansion. Now there are two different types of linear normal modes we can come across. One corresponds to the real eigenvalue, which will be one dimensional eigen subspace, and another consists of two complex conjugate pair of eigen vectors, which will give us a two-dimensional subspace. The motion on one-dimensional subspace, it is very trivial. So here in this work I will focus on the second case, where the normal modes will be either, for linear case, either it will be a two-dimensional subspace, or for non-linear case it will be a two-dimensional manifold. Now let us consider one general smooth nonlinear dynamical system described by equation number 3, which induces the flow phi, which tracks the evolution of any state variable in time. And in figure 7 I have shown the class of state points which evolves in time. Now in operator theoretic approach, as yesterday Professor Dimitris explained, in operator theoretic approach we are mostly concerned about something called observables, which are some measuring functions of our state variables, and the collection of these observables, they form a vector space, which is indeed an infinite dimensional Hilbert space. So the Koopman operator acts on this Hilbert space of observables and tracks the evolution of these observables in time. This operator has one nice interesting property, which is it is a linear operator. So we can always leverage from the linear algebra to solve this kind of nonlinear dynamical problems. So our objective is to find out the spectrum of this operator and use this eigenfunctions of the operator to parameterize the nonlinear normal modes, or as I have told that those invariant manifolds. So equation 5 shows that whatever I told just now, that the Koopman operator, it emphasizes the time evolution of any observable. It has this good linear property. Now there are some observables whose time evolution looks like this. That spatial and temporal function, we can like pull out the temporal from this, they don't, we can write it down separately. So this kind of observables are known as Koopman eigenfunctions, and they have pretty good algebraic structure. Like the leveraging on that, we can always create another, like we can always create another eigenvalue and eigenfunction from the other by composing the other eigenfunctions. Now I will not go into details in that because I don't have that much time. So the fundamental idea is to parameterize the manifold. For that we are using Koopman eigenfunctions, which some fundamental theorems of dynamical systems like Hartmann-Grobman theorem and Hartmann theorem, they these theorems allows us to use this idea. Like I have proved in one paper, in my paper, that from the corollary of Hartmann theorem, it can be proven that Koopman eigenfunctions resembles some diffeomorphism near the equilibrium point, and which will eventually help us parameterize the invariant manifolds. Sternberg theorem emphasizes that there exists some analytical manifold near the equilibrium, and it is unique, which is basically it needs two basic conditions. One is the fixed point have to be hyperbolic, and another is it have the eigenvalues have to be non-resonant. Lan et al., they extended this idea and showed that it can be, the global parameterization can be achievable. So the main idea is to transform the dynamics, represent the dynamics in some coordinate, which is zeta coordinate, and eventually represent it as a linear system. The coordinates itself are non-linear, but we can represent it as a linear system. I will show it what is the main idea behind this. The main idea behind is to find out some observable whose evolution will be exactly like the flow of the system. The identity function serves the purpose. Where I have proven that I haven't showed it here. I have proven that the Koopman eigenfunctions, they forms the basis of the observable space, and using that we can always use this kind of transformation, this kind of representation to this kind of representation for our purpose. Now from now on I will start going to like for some special like specific cases. Here I have considered some one 4-dimensional system, 4-dimensional state space where I have two normal modes. The schematic is represented here, and it is each of them are parameterized by these zeta coordinates. This should be the representation of any state variable of my system, and where these v, k1, k2, these are called typically known as Koopman modes, and the corresponding flow can be represented as this. So for experimental purpose I have used one double duffing oscillator with the underlying objective to check the accuracy of this framework on whether it is depends on how it depends on the internal resonance and the dissipation of the system. So these are the governing equations where I played around with the parameters, and there is one assumption that damping of each oscillators are same. This is the state space form, and after using that representation here I will end up these are the nonlinear terms I have showed there. After using this representation we will end up with this equation number 26, which basically from there the algorithm is to pull out all these coefficients zeta k1, zeta 1 k1 and zeta 1 zeta 2 k2 coefficient of these terms. We will have that polynomial expansion. From there we will get the coefficients of these terms and solve those linear equations separately to get each Koopman modes. So for that the first order solution will always give us the linear normal modes, the eigen solution. The second, in our case, we as we don't have any quadratic nonlinearity in our system, so we will not get any thing out of the second order solution. The first nonlinear solution we will get in the third order solution. Now it can be observed that there is a sparsity in this Koopman modes, like only because of the problem I have taken, as the nonlinearity is cubic nonlinearity, we will only get the modes corresponds to the powers of 3. So these are the parameters, around some 2 lakh parameter I have tested it, and there is one empirical measurement, empirical measure I have introduced, where we will measure the internal resonance. Like it is not like some binary thing, it is in resonance or not, it is not like that. It is some kind of continuous measure which I will show on this plane. If if the scatter is always on this line, it will mean complete resonance, and from if we measure the distance from there we can get the continuous measure. So this case represents the complete resonance. This is near resonance. We can see from the figure B, 13B, that it is somewhat near resonance but not complete resonance, and this shows the complete out of resonance. Now I have tested it in big parametric region, and this result came out that it shows that whenever the system is very close to resonance, the accuracy is always good. The correlation plot also shows the same. When they are very correlated, the accuracy is good. And the effect of damping, it also shows that when damping is very low, the accuracy is always high. So there are reasons for that. I don't have that much time to explain it. So these are my conclusion is like okay, I should stop. Like, thank you. Any questions?
Thank you very much. I don't think we have time for questions, but we can talk during lunch. So we can move with the last talk before lunchtime.
Hi everyone, my name is Prasad. I'm a master's student in Department of Applied Mechanics. So my topic is a little bit different from like I have seen from last 2 days. My topic is on pins. So pins is physics-informed neural networks-based approach to the analysis of reaction diffusion models. So our main topic is I have to solve the reaction diffusion equations with the help of AI. So first I'm going to give the introduction why we are going to solve reaction diffusion equation, and then a brief literature on what pins is. Then what problem statement I have identified in this, and then I will be going to conclusion. So what is reaction diffusion equation? So whatever patterns we observe in the nature, like from the sand dunes to the the animal skin, cheetah, zebra and all. So Alan Turing said that all those patterns can be described or generated from a coupled reaction, a coupled a PD. So where two species, for example U and V, they compete with each means they compete with each other for one reacts, one diffuse, and it will give rise to a pattern. So this is the general form of the reaction diffusion equation. So our main purpose is to solve this equation. Now the existing methods what we have is like RK2, RK4 methods and all. They are still good. I mean it takes more computational time and all, and we have to discretize it. So for example, so I will explain afterwards in the. So basically what is neural network? So I hope everybody has slight idea about it. I will give a brief intro. So we have the input, we have the input, and we have the outputs. So basically we need data, and we give the inputs, we get the output from the network, and then we compare it with our true output, and then we compute the loss function, and then we reciprocate that loss function. It is called as back propagation. So back propagation means that we are going to find that which weights and bias is more responsible for the loss. So accordingly we will tune that weights and bias, and our main purpose is to minimize the loss function or the loss value. So now physics informed neural networks is, now how should we incorporate physics inside this? So it has been done by Racy in 2019. So what he says that if we have the data and then we are going to solve something, so we have a large domain of solutions to look for, but if we have the physical laws with us, so our domain will get constrained. We will have to look for a very small domain for the answers. So these physical laws are mainly in terms of differential equations, because in neural networks and all, we mainly deal with the gradients. So it's very easy to to create a differential equation with the help of neural networks. So I will explain, and also the main purpose is it will require less data, because data is the main thing in the deep learning stuff. So if we know that it should mean some physical laws are there, so the amount of data required to minimize the loss will be less. So the basic algorithm is like, we will first define the problem, whatever differential equation it is, like ordinary, partial, coupled, like anything. And then the most important thing is formulating the loss function, because what Resi said is, what you do is you put the differential equation inside the loss function, so that our data, our model will adhere to that equations. So for example, if you see, and we are not going to use any external data over here. The only data we are going to use, it is like the differential equation itself. So here we can see we are going to compute the residue of the differential equation, and then that residue of the differential equation we are going to incorporate inside the loss function, like here, like this. And then we also going to use the boundary conditions inside the loss function to like as a data, but no external data has been used. Then okay, I will explain it afterwards then. Yeah, so the problem statement over here is Resi described, okay, we can solve the differential equations with the help of pins. But the problem with that is it can be solved for a very short amount of time. It cannot be solved for the longer time. Now, if we want to see the patterns in reaction diffusion equation, and also we need to solve those for a longer time. So there is my first problem statement, how to, like, is pins capable to solve the any simple model like oscillator for a longer time? So the answer is no. Like, if you see after 2.5 seconds, our model is not able to capture the complexity of the complexity of the oscillations. So the reason is like we are only going to use the differential equation and the condition which we have. So if we see, we only have the data at t is equal to 0. So it will get trained up till t equal to 2 seconds and all, but after that it's not going to happen. So the partial differential equation which we have incorporated inside the loss function, it will just make sure that the oscillations are close to the mean, but still it's not going to train. So what, like, logically we can think is that what we can do is, for example, what we can do is like, okay, now here it is giving good results. So what we can do is we can get the output from here, and then we can again take that as a data to the model and train it. So this is an algorithm for that. Like, we are going to train the whatever t is, we are going to make it short in short parts, and then we are going to train the model for a short time. But the only problem, like over here, is then we have to train it for every small intervals, and it's not fair. Like, it is going to take large computational cost and all. So what we are going to use is, last year one DeepNet named model came into picture. So there we have the flexibility to not train the model again and again. So what DeepNet is like, DeepNet has two structures, one is the branch and one is the trunk. So how I exploited for this is like, for like this trunk will take care of the differential equation. So differential equation is end over here, and like the basic phenomena is we want to train weights and bias as that like our loss is minimum. So so the thing is like, from here we will put the data which are going to, like, for example, from 0 to 1 we are going to train it then like this part of the section will not get trained. Only this part we are going to put the data which we have got at t is equal to 1. It will go over here. So we don't have to train the entire model. We are going to train only the smaller part. So the entire back propagation will not happen. So these are some example which we solved with this, and we were getting excellent result till t is equal to 20 seconds and all, and it can go until how much seconds or t you want, but the only problem is for more time you want to train, it will take the model will take more time to train. So here it took approximately 3 minutes, and loss came out to be 1.26 n raised to minus 4. Then underpole oscillators, duffing oscillators. So all equation can be solved with this. But our main goal was to solve the to the reaction diffusion equation. So this is one of the reaction diffusion equation I solved. This is a single component, so we can't see any pattern in this, because if you want to see pattern, it should be 2 component reaction diffusion equations. So this is how we solved it, and with the same algorithm, with the same depot nets, so we were getting accurate result with this. So this is the graph where it shows that how with each iteration the loss is going to minimum. So it took around 10,000 iterations and to get the loss to this range. And the problem with the coupled equation was, like in the coupled we have 2 state variables u and v, and we have same weight and bias. So and in the reaction diffusion equation, the u and v will show like kind of opposite phenomena. So the same weight and bias will not be able to give output for both of them. So what we did was, right, we create a composite neural network, inside which what we do is the weights and bias of the neural network 1 will take care of the u, and the weight and bias of the neural network 2 will take care of the v's phenomena, like the complexity, oscillation, all those stuff. So this is the Gray-Scott equation we solved, and so yeah, we got the patterns and all by solving this. So this is the plot at t is equal to 1/500 seconds. The problem is the training took almost half an hour, and the loss was also pretty high. It's 2.5%. So yeah, our next future work is like we are going to work on this to make it minimum and all. And the next we solved was Gerard-Enhart model. So it was quite complex model. Here we can't see like pattern that visibly, but yeah, we are getting in pattern here as well. And here this model took around 1 hour to train. So like the conclusion is like pins were not able to do the justice to reaction diffusion equation. So we created the physics informed depot nets and the composite neural network combination to solve this. And once the model is trained, the reaction diffusion like we can get it, like results in like really fast. But the only problem is we have to train it, and yeah, this method suffers from errors of dimensionality. Like for example, if we go from 1 dimension to 2 dimension, the training cost will increases a lot. Yeah, that's it from me. Thank you.
Thank you very much. Is there any quick question for this talk or for the previous one? If not, let's thank the speaker.
Okay, it's time to start. Welcome to the third afternoon session of the conference. Our first plenary speaker of the afternoon is Jinqiang Duan from the Great Bay University in China. And he going to talk about data-driven stochastic dynamics, extracting governing law, and predicting critical transition. So Jinqiang, when you want.
Thank you very much, everybody. In the next 40 minutes, I'd like to share with you my excitement in extracting stochastic governing equations and predicting critical transitions in stochastic dynamic systems. So our story is about critical transitions in stochastic dynamic systems. Often, this is called the tipping phenomena. So this is a popular book by Martin Scheffer about critical transitions in physical science and in social science. And the tipping really means the tipping over there. You see that remark. But I'd like to show you some specific examples about critical transitions and the tipping. So this is this is about climate change. This is the data about temperature, although it's based on carbonate carbon. This was the temperature in the time of 60 to 62 million years ago. As you can see, there are two tipping points here. There are two abrupt, quick transitions during this 20 million time period. Now the transition time is very short, or at least it's a finite time. Okay, and now in this time series, you can think about this is a small oscillation, and this is a big jump. Okay. Now the second motivation coming from biophysics. So the gene expression has two components: transcription and translation. The transcription right now can be well studied quantitatively because of the single molecule techniques. And that's the part that I would like to show you. And that is a transition process. So in order to follow the process or the progress of gene expression, one way is to follow the concentration of a transcription factor, a special protein. And this special protein can be measured. I mean, the relative mass or the concentration can be measured. So this figure shows. So this figure shows two measurements. The blue one. So let's look at the blue one. The other one, the black one, is for the other method. So in this blue one, there are 5 samples. It shows this concentration of one protein during the transcription of one gene in this paper. Goes quickly from 0.2 to 0.6 in 500 milliseconds. So this is a finite time transition, quick. Now, motivation 3 is related to my recent interest in brain science. So this is data, EEG data for epilepsy from a specific, is real data. And we call biomarker for epilepsy is an EEG signal. Now this data coming from 4 locations, 4 channels, 1, 2, 3, 4 channels. As you can see, each time series or each EEG signal shows a sort of steady state. Not quite steady, but maybe you can think it is a metastable state. It quickly goes to a big oscillation. Think about it as a metal periodic state. And now you see, there's on each location or on each channel, there is a quick transition. It shows the onset of the seizure. So in all these 3 motivating examples, we see there's a tipping and there's a quick transition. And the issue is how to understand this transition, and better if we can find a quantitative indicator that we can predict or say something or detect the transition. Indicator is the indicator that we heard many times in this conference, like the Lagrangian descriptor is also indicator. Biomarker is a biophysical or biochemical correspondence of the indicator. Indicator is more mathematical, more quantitative. Biomarker is the chemical or biological thing underneath it. Now, how to predict the critical transition from our everyday experience? When we feel we are about to get sick, we often feel it. This is the temperature curve during the 24-hour time. This is a typical one. It goes from the morning and it goes to afternoon. But the highest one is close to 37.5. If you go beyond 37.5, then we know we need to take medical attention. Now, what do you see here? We see there is a curve here. You see there is a curve. We follow a curve, a time evolutionary curve, and then by looking at the geometric shape or geometric property, or measure the temperature following the time, we can say something about the tipping and critical transition. So here there is a biomarker is the temperature, molecular motion, macroscopic description of molecular motion in our human body. Indicator is the thermometer. Temperature evolution curve, there's a T of small t is a curve. Early morning, we need a tipping point, it's the threshold, 37.5. That's the insight I'm going to use for the rest of the talk. So this is a dynamic phenomena because there's a time evolution and there's a quick change, finite time change at least. There's a critical threshold. That's the one we like to say something. Okay. Now, there are other relevant issues about tipping points. For example, bifurcation. We heard in this conference multiple times. A bifurcation is a tipping in a parameter space. But very often we like to look at the tipping in the state space. In the stochastic dynamic systems, sometimes we also look at the tipping in the space of probability distributions. So this more traditional concepts all have its place in tipping or critical transitions in what I'm saying in this presentation. So can we say something about the critical transition, the tipping point? Certainly, this is a dynamic system issue, and the dynamic system framework should provide some guidance for what we are going to do. For dynamic systems, in this conference, we have heard about invariant structures, manifolds, lobes, and Hamiltonian islands, attractors, foliations, heterokinetic orbits, and so forth. Periodic motions are often related to the time series that we see in data sets. Prediction is a fundamental issue in dynamic systems. If we don't do prediction, we don't do dynamic systems. Now, I still like to mention that eigenvalues, the upper exponents, and topological index like counter index, which I like very much, are also indicators we often use. But very often, this works very well in linear systems. But counter index is for nonlinear systems, but it's hard to use. But nowadays, people are thinking about the computational methods to look at the index and things like that. So there are some interesting progress going on here. I mentioned that we need a dynamic systems framework. So dynamic systems will have autonomous systems, non-autonomous systems. So let's look at the autonomous system. So this is something that may be related to the transition that I mentioned from a steady state to a periodic oscillatory state. This is the one that resembles that phenomena. But look, from a steady state in the middle to the periodic limit cycle, this transition takes infinite time. But I mentioned finite time, short-term time, many times. So this model will not work. And how about this one? This is also a two-dimensional system. It has a steady state, and this dashed closed orbit is unstable. So there's an unstable limit cycle. And this blue one is a stable limit cycle. So this is something like there's a saddle in the middle. So this is a two-dimensional double well system. Now, think about the transition from a steady state to a periodic oscillation in blue color. Can that happen in this two-dimensional autonomous system? This cannot happen because that, if it happens, then this transition will cut through this closed orbit, unstable one. So that will violate the uniqueness. So this tells us that we need to think about a non-autonomous system. If we like to use dynamic systems, or if we believe dynamic system, that systems are the right framework for the critical transition. So naturally, people think about non-autonomous dynamic systems. Yesterday, I mentioned that non-autonomous systems are too difficult for me. Stochastic ones are easier. So that's why I think about a stochastic framework as a special non-autonomous dynamic systems, and use this setup to look at the critical transitions. And other people are thinking the same way. For example, this book was old, 1987, noise-induced transitions. So other people already noticed that we needed to look at the transitions in a non-autonomous way, especially stochastic way. And later on, in 1990s, Ludwig Arnold also put things like this in a more abstract framework. So stochastic or random dynamic systems, we are doing similar things that we had been doing for deterministic dynamic systems. We have geometric subjects, and we have geometric topological probabilistic methods. So the only extra is probabilistic methods. But even for deterministic systems, like yesterday's talk, Monday's talk by Erica Bolter, also use the probabilistic methods. But today, I'd like to focus on the transition in the short time, critical transition. A short history on stochastic dynamic systems. Also, stochastic dynamic systems, also stochastic calculus is 300 years later than deterministic calculus. The stochastic differential equations are only 20 years behind ordinary differential equations. I just talked with Steve Wiggins. The well-known book by Hartman Levinson on ordinary differential equations was the final edition was fixed up in 1955, and the textbooks for stochastic differential equations were pretty much settled down in 1970s. However, the dynamic systems ideas for stochastic differential equations settled down only in 1980s, and especially the subject that influenced me is by Adam Nielsen's stochastic mechanics. And one reason for that is I was exposed to the geometric mechanics while I was doing the postdoc at Caltech with Steve. So this influenced me on getting into the geometrical way or dynamic system way of looking at stochastic differential equations in 1990s and beyond. So there are some interesting things happening right now, including the data science methods for stochastic dynamics. And today's talk is only a tiny part of that. Let me remind you about how to model the noise. The Brownian motion is the light tail. It has light tail distribution, also called a Gaussian distribution. It is used to model the Gaussian distribution, Gaussian fluctuations. For non-Gaussian fluctuation, this was mentioned in Chen Nan's talk yesterday and on Monday. It's a fat tail. It has fat tail distribution. It's non-Gaussian, and it's one typical model for non-Gaussian fluctuations. Being non-local, it has jumps. and the jumps are modeled by a Borel measure. It's called a jump measure. Now, according to Leffler-Eaton decomposition theorem in stochastic calculus, every white noise can be decomposed into two components. One is Gaussian noise, Brownian motion. One is non-Gaussian noise, Leffler motion. So that's why we have a sort of standard or generic format for stochastic differential equations, which are models for stochastic dynamic systems. So whenever we say stochastic dynamic systems, it could be an ordinary differential equation, but now for this case is a stochastic differential equation. Okay, and often in literature, because this one is hard to deal with, so people only see the Brownian motion. But actually, this term should be there. This is sometimes it's invisible, but according to Leffler-Eaton, that term is there. So the question is, I have data. I have the sample path data, the system state data for system evolution, the data for states. So can we extract a underlying stochastic governing model? Can we get a stochastic differential equation out of it? If the noise is only Gaussian, this has been known for about 40 years or so by Kreimas and Moyer. So if we ignore the non-Gaussian noise, then the Kreimas-Moyer formula says there's a relation between the observation on xt and the coefficients. This coefficient is the vector field, and this coefficient is the intensity of noise. So once you have that noise, you have that relationship, you can go from the sample path observation to the coefficients. So that provides a way to extract the underlying model. It's as simple as that. Okay, now if this is the Kreimas-Moyer formula. So the left-hand side is based on the data, xt. The right-hand side is the vector field and the noise intensity. Okay, so this naturally gives us a way to find out the underlying stochastic equation if you only have noise, if you only have noisy observation on the state. If the system includes the non-Gaussian noise, as I said, this is the typical generic situation. And recently we derived a non-local Kreimas-Moyer formula. Non-local means in the formula there's a spatial integral. So in this case, we have vector field, noise intensity for Gaussian noise intensity for the non-Gaussian noise, and I also said if it's a non-Gaussian noise, there's a jump in the sample paths. So that's why I need a jump measure. Jump measure is a part of this Leffler noise. So the new formula derived recently is the relation about the sample path data and the coefficients in the differential SDE. There's an integral here, so we call it a non-local Kreimas-Moyer formula. So as long as we have data, we can write out the data under the assumption that you think that this stochastic model is generic enough. Okay, and you have seen many recent works on extracting ordinary differential equations from data. So this includes the non-Gaussian fluctuations, and some of you might have already realized this is a high-dimensional problem. So you probably also think about a quasi-Monte Carlo, and which is a terrible thing to do. I know Kevin has done that well. It's hard to do. So recently, in the progress in the data science, there's a new method called a normalized flow. So that's why we use the normalized flow to do that. But still, we need to improve that one so that high-dimensional extraction can be done more smoothly. Now the next part of my presentation is how to find the tipping point in a critical transition. How to detect the critical transition and the threshold. So this is the second part, and this once this is done, then I'm done. So critical transitions can be caused by a parameter change or environmental fluctuation or maybe the interaction of internal components of a complex system. It can be caused by something that we don't know, but it shows up in the data. We like to detect that out. So this is the model that we have. We think there's a model underneath it. And if you don't like noise, then you say, okay, let's take the noise out, and then you have then divided by dt, then we'll have the stochastic dynamic, and we'll have deterministic dynamic systems. Then all your techniques here are applicable. Okay, now I still like to go back to the inspiration from the human body temperature. We have what? We have a curve, evolutionary curve. It goes on in one significant time scale. For example, for the human body, it's 24 hours. In other physical systems, they may have an underlying physical time scale. So there's a curve. And following this curve, or this curve in dynamic system, the curve means a trajectory or an orbit. In stochastic dynamic system, we also call a trajectory. So this curve, how to find out the tipping by following a curve like this, either geometrically or topologically. Yeah, you see the shape. For example, if the slope goes too vertical, then something is going to change, right? It indicates something goes too fast. If it has some topological change, that may also indicate something is going to happen. If you bypass a saddle, you may also think out that this saddle may, or saddle means there are unstable directions. It may push your dynamic system and go into some other undesired direction. So by following the saddle, that which we often do in the deterministic dynamic system, we may be able to do something. So by looking at a special trajectory in dynamic systems, where by looking at the topological and geometrical features, we may be able to think out the tipping point. This is one insight we learn from here. Or we may have a device, a medical device, or which means mathematically means an indicator. Maybe you compute the indicator by following this special trajectory, and if the indicator shows an alarm, that may also indicate something. So that means we have a topological way, topological geometrical way, or we may have some analytical indicator that help us to gauge into the system to find the tipping point. Now I'd like to tell you, to find the tipping point and to detect the critical transition is a hard job. I'm not saying this is a simple job. I mean, this is only the insight that I have, and I'm going to follow this insight and do something to share with you my excitement. Okay. Now there are two. We have using two indicators to detect, to predict critical transition and think out the tipping point. The first indicator is based on maximal likelihood trajectory. I mentioned that we follow a trajectory in dynamic systems. Well, in dynamic systems, the fundamental object is a trajectory. So I like to do something following a trajectory. Often it's a special trajectory. So the first indicator is by using maximal likelihood trajectory. Second indicator is about on-target matching up action functional. I mentioned in the inside I said we can use a device to calculate something, and by looking at the values of that indicator, we may be able to find out the critical transition. So I'm going to show you these two in two examples, and hopefully maybe we can keep talking, and someday we may have a better theoretical foundation for the indicators that I'm excited about. Once I finish these two indicators, I'm done. Okay. So first indicator, well, we talk about the metal stable state. So for this work, which is a equilibrium stable state without noise. once the noise is kicked in, then this stable point will probably wiggling around a little bit. So we call it as metastable, which is a concept in physics. A metastable oscillatory state is like in the time series is this oscillation, quasi-periodic, but it's not quite quasi-periodic. So we call it metastable oscillatory state. Maximum likelihood is a reference trajectory, like the temperature curve that we just saw. It's a reference trajectory of this dynamic system. Hopefully, by looking at this maximum likelihood trajectory or pathway, we may be able to get something about the critical transition and the tipping point. Okay, now, so this is the model we have. For a stochastic differential equation, we have a Fock-Planck equation for the evolution of probability distribution of individual trajectories. So this Fock-Planck equation with the generator A. This generator A is also called the Frobenius operator, transfer operator, or also called the Markov transition operator. So it has different names. This generator often is a differential operator, like a Laplacian, for example. But if you have Levy noise, the long Gaussian noise, it has a long local integral term. So this generator A in general is a long local operator. So this is a long local Fock-Planck equation. Okay. So we have the probability distribution for individual solution paths given an initial starting point. Now we are talking about the transition from one state to another state. In Steve Wiggins' the language is dynamic regimes with quantitatively different dynamic behaviors. Okay, so there are two regimes. We like to see the transition or the likelihood for transition, likelihood for the tipping. Okay, so we can figure out this conditional probability density. What is the condition? Condition on initially at this metastable state, and finally TF final time is at another metastable state. So the condition on a given time period, 24 hours, from one state to another. Often these two states have physical meaning. So therefore, we like to see the transition between them. This can be derived by using a conditional probability formula. So this conditional probability, if the conditional probability is highest, that means it's more likely, right, at each time. So if we evaluate the mode of this conditional probability density, mode means the plateau, is the highest probability. So if we find the plateau or the mode at each given time, we also trace out a curve. So this is like a probability density, conditional probability density, but you only walk on the top. Okay, so this is the max. This gives us a reference trajectory or maximum likelihood transition pathway. Okay, now so we have a curve, just like the temperature curve I showed you one moment ago. There's a curve. This curve certainly carries the maximum likelihood about the transition. Okay. Now, if this likelihood, likelihood is very flat, then you want to go to the target we are interested in. So we like to see the slope. For example, if you look at the geometrical meaning, if the slope goes far, slope goes up quickly, then there will be more likelihood to go to the second metastable state. So this is one definition for the tipping. So this is the one quantitative way to look at the tipping. So when the slope is bigger than 45 degrees, for example, you can use the if you like to have an early warning more in advance. If the TP is to 40 degrees, you can start to do early warning. So this is a relative threshold. Okay. Now let me show you an example in this conceptual stochastic energy balance model. This is an energy model that we used in climate dynamics. So this is the temperature for the Earth. This is a highly simplified model. Okay, and it includes the planetary albedo and the heat capacity and the sensor and other constants. But in this paper that I mentioned, in this paper, our goal was to test if a special extreme event like a non-Gaussian jump, will that induce a climate change? That was our underlying thesis or goal to examine. But here we don't. Here I only want to show you how to do the TP. So for this one, I already have the data, so I don't have to go to get the data from get the model from the data. If you have the data, for example, the I-score data, you can extract a model like this, like Peter Dieterfinsen in Denmark. He was trying to do that. So then I can compute the conditional probability and the maximum likelihood transition path. And so you see, when there's this slope goes very vertical. It's not vertical, but it's almost vertical. So it's like 80 degree or something. So certainly more than 45 degree when the slope is 1. Okay. So in this case, this is the two different extreme, the two different non-Gaussian fluctuation input. Okay. So there's a tipping point here. So this appears to tell us that it can tell us that for different noise, for different non-Gaussian extreme events distribution, the alpha index indicates the non-Gaussianity. So we have a tipping point. It changes with the external stimuli. Yeah, that was the idea for that paper. Not actually saying this happens, but if it happens, it will change like this with the noise. That was the purpose of this paper. So this is the first indicator, and showed illustrated in a simple conceptual climate model. Now the final one, second indicator is I have a special reference trajectory, like a dynamic system trajectory. I don't look at its geometric or topological feature. Instead, I evaluate something. I compute the entropy, for example. But this time, I'm going to compute a Lagrangian action. As for people knowing statistical physics or classical mechanics, Lagrangian action it indicates significant sense. It gives us the equivalent dynamics of Newton mechanics. Okay, so to fix so let's do it in a simple system without a napping noise, just Brownian noise. So this is a vector field. My notation changed. Sorry about that. This is noise intensity. So this is a stochastic system. I thought this was a one-dimensional case. Now, so the Anzak Mashinov action functional. This was introduced in 1953. It was used by Anzak and his PhD student about the most probable transitions in statistical mechanics, also between two possible metastable states. So this Anzak Mashinov action functional gives us the probability for that transition in a tube surrounding that reference trajectory. Okay, so this is the time t is the transition time, often determined by other physical mechanism. If I change this t to the small t, to the current time, not the final time, then I'm following the trajectory with action functional, with action values. Okay, now this can be done in neural networks for high dimensions. But I'm doing this with a one dimension, so I really don't need the neural network. But for high dimensions, our students can do this with neural networks. Okay, now this is the real data. Epilepsy of EEG is not our data, it's data is from a public data set. So this there are I think 23 channels. At each location, as you see, they are onset of seizure. See, first onset, the second onset. So let's look at this, the first onset, around 500 in the time. Okay, so so this slide shows that if it's a higher dimension, we need to do. If it's a higher dimension, we can use the we can do the nonlinear reduction. Nowadays it's called a diffusion map. One way is to do it by diffusion map developed by people, by a group of people surrounded by Kaufman, Kopakidis, and many others. So a special version of this diffusion map is the anisotropic diffusion map. That means you also the kernel is not only Gaussian, but you take some non-Gaussian effect into account. So that means your data is not so Gaussian. But if it's non-Gaussian data, you think about you do something else. You include something with this so-called directed kernel. Okay. Now this is a standard technique now by projecting into the eigenfunctions. The first eigenvalue is also 1, so it's not significant. The second one usually is dominant. So the third one may be also. So you project the data into the first few eigenmodes. So you have a finite dimensional system. But because the data is stochastic, so we are going to use those finite modes, and then we extract the stochastic model as we did in the first part of my presentation. Okay, or better off if the dominant mode is only one mode, then you have a one-dimensional system. Then life will be easier. Okay, so for example, we did this with a 73-dimensional system. We project into the first eigenmode. This is the system evolution on the first when the system is only projected to the first eigenmode, and we can derive we can extract a stochastic differential equation by using Kramers-Moyer formula. Okay, Kramers-Moyer formula gives us information about the data, the sample data, and the coefficients of a stochastic model. Okay, so for in this case we did a one-dimensional reduction. You may say this is 23 dimensions. You did a one-dimensional extraction. We can do higher dimension, but it's just more involved. Another reason is you see the separation of eigenvalues. So first eigenvalue is also 1, second lambda 2, lambda 3. If lambda 3 is well separated, then you can do the one-dimensional one. So this is like for this community, this is something like a slow manifold or elation manifolds. If the dimension is lower, you project to lower dimensions. Yeah. Okay. Now, then what to do? We have a one-dimensional system here. We have a one-dimensional system. I have the sample path data. Then I use Kramers-Moyer formula. I get a one-dimensional stochastic differential equation. Then I can use the Onzaga meshing up formalism to compute the most probable transition path from an EEG signal. From the EEG signal here is the steady state to this high. So I like to see the transition. Now this part is based on Onzaga meshing up theory. That part is well known. Now our part is what? Our contribution is you have a curve. I have been talking about the curve. Actually, I should say trajectory, dynamic trajectory. We have a dynamic trajectory. I also have the Lagrangian action functional. Now, in this stochastic case, it's not a classical mechanics, so we call it Onzaga meshing up action. It changes with time. we compute this action value to see if it tells us something useful for critical transition or tipping. Now let me show you what we have here. Right on time. Okay. Okay. Now look at this. Look at the green. First, look at the green curve. The green curve is the variance from the mean, which is the most primitive way to look at the detection of critical transition. So look at the variance. If variance is big, there's a transition. Medical doctors know that. Okay. Now, but from this data, look. There's a onset of seizure or epilepsy here. There's a lot of one here. Roughly, there are two onset, two tipping points for the disease to come out, right? For the seizure, for the epilepsy. In this case, actually, this variance shows two high points. So the variance tells us something, right? Tells us something. But now look at our on-target matching up action function value. It shows a high point here and a high point here. And it indicates something there. Yeah? It indicates something there. Maybe we can do a higher dimensional approximation, then this prediction may be better. So this is one thing we have been working on. And of course, this action function its importance is well established in non-equilibrium statistical mechanics. Okay, so that part is not from our dynamic systems. So that's why we have some belief already. We know this one carries information. So and we calculated that in this example. It indicates that's interesting indeed, and I think it's better than a classical standard deviation or variance prediction. Yeah. So finally, in conclusion, we have long Gaussian data from a stochastic system. The equations are often unknown. What we can do, we derived a non-local Kramers-Moyle formula. With that, we can find out the model. That means one model. Well, inverse problem is never unique, but this is one model for which fit well with that model. And tipping, which is a threshold value for critical transition from one regime to another with qualitatively different dynamic behavior. And we introduced the two indicators, tell us for the early warning of the tipping. And thank you very much. Happy birthday again.
Thank you very much. Very interesting talk. Are there any questions?
Yeah, thanks for a very nice talk. So can I ask, do you have the uniqueness of this maximal likelihood trajectory?
Okay, very good. That's a good question. So when I calculated the probability, the plateau. How about if we at one given time it has two plateaus? Numerically, we don't have the equal thing, but in theory, they could have two. So in that case, we have to make a choice about which one to use. So in that case, I think there may be a ambiguity about which trajectory to choose. In fact, some years ago, I have a PhD student working on the maximal likelihood phase portrait for stochastic dynamic systems, and that thesis talked about this kind of choices. Is that, I think, a relevant question? Is the choice of maximal likelihood trajectory impact the prediction of the tipping? For that part, I don't know. Let's write a paper about it.
Any other question? I have a question. You have presented two indicators. Is possible to know a priori where an indicator go to work better if we have some data?
Yeah. So this basically we have a model because we extract a model from the data. So we're going to use that model for the next stage as a prediction. So this is the hope. Maybe I think your question also relevant. Maybe the data assimilation can be put into work. So when you have real data, I can fit in, so to improve the prediction. That should be interesting.
Okay, thank you. Well, let's thank to Yaka again. Thank you so much. Our next speaker is Yania Hu. It's a contributed talk. Yania Hu comes from the Delft University of Technology and the Beijing Institute of Technology, and the title of her talk is Large Deviation for Coarse Ingersoll-Ross Processes with State-Dependent Fast Switching. When you want.
Okay. Okay, thanks for your introduction. I'm glad here to give the presentation. So this work is joined with my supervisor Richard and Fubao. So the title have already introduced, like large division for a model. The model exactly is a slow fast process. Okay. So at first I want to introduce the motivation. Many talks before me introduced many background of the slow fast system. And the first one is the weather climate model. We think the background we already know. So I continue to say maybe the chemical reaction is also the model. In this process, they have the slow process and the fast process. Maybe they will interact with each other. And also in the stock market, okay, CRR model is one of the SDE to describe the stock market. So some investors want to see the long-term behavior and then they make decision. But some people, they want to know the very, very short time and then make the decision. Okay, what is the key character of the slow fast system? I think it's a scale separation. So in detail, the fast process can quickly get the state, but this depends on the slow process. The slow process also involved by averaging the coefficient of the faster process. So we have a slow faster process. This is very complex. And then by averaging principle, we get a simplification process. But the simplification process can include all the information of the complex process. Okay, so we want to know how to estimate these approximation errors because the simplified model. Large deviation. Okay, what is large deviation? Large deviation is want to study the real events that decreased at an exponential rate. So informally, for math, this probability stands for the real events. They want to know the probability of this event in the exponential rate. And the rate I is called the rate function. Now I want to I want to introduce some relative work studies slow fast system, but they focus on the large division. At first, He and Yin and Zhang, they studied the slow process. No diffusion means ODE. And the fast process is just a Mark function. This Mark function doesn't depend on the slow process. And then the second, Kumar and his collaborator studied also slow fast, but this time it's the jump diffusion. Okay, and Duan also explained this means non-Gauss. And when they prove light division, they use the method, it's nonlinear semigroup method, but they should give a assumption for the compare principle. And then but hierarchy, they use another method called the weak convergence method to study light division. If they use this method, they should know the environmental for the faster process should be Lipschitz continue. And then Karaji tried to study light division for slow faster system, use the nonlinear semigroup method. They don't give the assumption for the compare principle. So during this paper, they use the main technology is the compare principle for HJB or HJ equation. And also the guy studied this kind of model. So obviously this is slow, this is fast, but both process I continue. So based on this reference, I want to study the degenerate diffusion. And I want to study the first is continue and the second is a discrete coincidence model. We can say this is a good example I found, I think, yesterday to explain the traffic signal control system. Okay, this is my model. So first is CR model from the stochastic market. And then this part is just holder continue. So let this process just work on a non-compact space. And my switch process is continue Mark function, but this part depends on the first process. The first process also depends on the second process, maybe called coupling. And the yellow part stands for the rate. So this time we don't know who is fast, although they are very small, but we should analyze. Okay, E is for the domain of the CR model, it's a non-compact, and this is finite, so it's compact. Okay, this is the model. We can think the traffic signal system. This part is like red light, yellow light, and green light, and the car move according to the CR model, and then at a random time switch to another, the light switch to another state, and the car still move according to the CR model. Yeah, in this way. Okay, now we already have the models. The first thing we should average the model, become a simplified model, is this one. We can find the coefficient is averaged by the stationary distribution of the fast process. Okay, remind this limit equation. This is very important because this is very, very important to get light division. So because we study the slow faster system, we assume if the faster system is very, very fast, okay, the slow process just stayed in the initial point. At this time, we can get the Danskaya-Adam light division. The rate is this one. This one is depend on the generator of the faster process. Again, so we assume the slow process remained stationary. Then we can get the friendly venture light division, means small noise pass light division. Here is the rate function. If at this time we let the rate function equal to 0, then we get this part is 0. So for the limit equation, it's here. So limit equation is very, very important. If I can't get the limit equation, so I can't continue to study the log division because there is a read function I need. Okay, so second, I combine the two types of log division, and then by calculation, I get this one. So now I want to know what is the best rate for the log division. Okay, I think there are 3 cases. At first, I just record the important formula. In the first case, epsilon and 1 over epsilon both very small, but larger than 0. So at this case, we can get the rate for log division is 1 over epsilon. And then at the case y, because n epsilon here is smaller than 1, then we can get the convergence. Convergence to this is a read function just the down square down log division. Okay, this is similar. And for the third one is epsilon equal to 1 over n. At this time, they compile the 2 read function. This is our main result. So how to prove the log division? I want to start to a famous Brazil formula. So if we want to prove the log division, we should prove the exponential tightness, and the limit is very, very important because the limit is in the read function. Okay, remind the take a look at the blue part, and then we continue. So this is also some idea need to recall. We first define a linear semigroup, and then from the linear semigroup, we can get a generator. It's called AN. If AN converges to A, and A generates a semigroup Sn, Sn is not other things. Sn just the limit or Sn. Okay, do the same. Fun and curse do the same for the nonlinear semigroup. Okay, this one this one is similar from the Brazil formula. So at this part, we have Vn when it's nonlinear, and then from Vn we get Hn. Okay, at this place we explain Hn convergence to H, and H generate a semigroup Vt. So Vt is very, very important to get the log division. Yeah, but this case is nonlinear case is difficult. So now I just conclude a little the method. The method is called a nonlinear semigroup method for proving log division, and we should prove exponential tightness because CR model is now compact. And then I want to know there exists a H, and H can generate a semigroup V. V can help us get the log division, get the read function. But recall the formula before. This V is a solution of the informally is the HJB or HJ equation. It's difficult to solve, so maybe we can't get the classical solution. Maybe we can just get the viscosity solution. Here I just want to summarize some important idea for the HJB equation. HJB equation arrives from the dynamical programming theorem, and the viscosity solution of HJB equation relative to the read function, yes, and the log division are connected to the wear post of the HJB equation. And we try to prove this in our case in the Holder continue case. So the future direction is 2. The first one, our state, just the finite state. It means compact And then we want to explain it to infinite faster switching. And then we want to extend the slow process to the real manifold space and continue to study that division. Maybe the model is more general. Okay, that's all. Thanks for your attention. And happy birthday to Steve.
Thank you so much, Jan. Very nice talk. Are there any questions? I have a question because maybe I lost something in the first part of your talk. In some moment you say that the process is stationary. Could you explain a little bit about that one? It's around the 11th slide.
This? This?
In the 11, sorry.
Oh, 11, okay.
The X and 11?
Yeah.
More, the X and epsilon, in some moment you say that you need that the process become stationary. The other direction, sorry.
Where? This?
Forward. More. It's not we could talk in the coffee break.
Oh, there.
Yeah.
Oh, this one.
No, the next one.
Oh, next one.
One more. Yeah. In the first part, you say you suppose that the X and epsilon remain stationary.
Yeah.
Could you explain a little bit this one? Why?
Yeah, because the fast process is very fast, and then the fast process at the long time behavior of the fast process is stay in a stable state. So this time we just can study this one.
Okay. Thank you.
Thank you.
Are there any other questions? Well, thank you so much. Let's send the speaker again. And now we have 30 minutes of the coffee break, so we come back at 4:45. Let's continue with the last talk of the day and the last talk of the conference. It's a plenary talk from Yanis Kevrekidis, sorry, from the Johns Hopkins University. That is online, as you could see him. And he got to talk about some old and some newer perspectives of data-driven modeling of complex system dynamics. When you want, you could share your slide.
Okay, I did start sharing. Does it show up?
No.
No, hold a moment. Now it should.
Now we see your, all your screen. Now, perfect.
Good. Thank you, Macrina. So, hello, everybody. As you see down there at the last line, it says, Madrid, I wish. I was hoping I can come, but in part due to family and in part because it's difficult to travel internationally while I am at DARPA. I couldn't make it. And as I told Macrina, I still dream about the tapas streets in Madrid. But I would like to be there with Steve. As I said, I say some old and some new thoughts. And Eric showed some old pictures on Monday. And so here is an old picture that I found. It's interesting to look at the subjects: full face, eyeglasses, outdoors, boats and boating, eating and drinking. Woods Hole, Massachusetts, that's a suggestion. I think everybody recognizes that Steve is the guy on the left. I'm not so sure that everybody would recognize me as the guy on the right. But it was 1991, and it was the last US-Soviet chaos conference. There were no Soviets after that year. And I think I first met Steve in Phil Holmes's office at Cornell in 1985, I think, or 80, yeah, I think so. And then we met he invited me to be part of the Journal of Nonlinear Science in Santa Barbara, and we've kind of been in parallel lives for many years in what he has done and what I have done. We've used his books, we've talked over the years, visited Bristol and Princeton and Caltech and back and forth. But anyway, what I would like to do, since we're talking about also in part about old times, I would like to talk about some old stuff that is kind of fashionable again today, and some more modern things at the end. And if you feel, please interrupt. This is kind of more of a discussion. So this is a paper that was written the year of the photograph and was published the next year. It has a very weird title: Discrete versus Continuous Time Nonlinear Signal Processing of Copper Electrode Dissolution Data. And it was based on experimental work in the lab of Jack Hudson in Charlottesville. And what the problem was in 1992 was that we had time series from experimental dynamical systems. So this is kind of a simple experiment. You take then you put it in hydrochloric acid and it dissolves. So we sold it as corrosion. You have a potential between the metal and a counter electrode, and depending on the potential, and now you can see at the top row time series for different values of the potential. The potential is the number on top. So you can have, like, straight lines, nothing happens, so steady states, and then you have oscillations, and then messier oscillations, and more messy oscillations. And at the bottom, you see the Takens embeddings of these time series. So you have fixed points, limit cycles, period doublings. Bottom left, you can even see a period 4, and then you see MS. And the point was, how do you do data-driven modeling based on time series for a parameter-dependent dynamical system? Well, you do what you do today. We did back then. You use machine learning. But first, one interesting thing is that you have a single time series, and if you have chaotic behavior, well, you need at least 3 variables. So what variables do you use? What is the right latent space? So where good latent spaces come from? They come from having a systematic hierarchy. If you have a cloud of points, you take enough moments to approximate the cloud. Sometimes they come from experience or expertise. And for maybe 20 years now, they come from data science. You can use techniques to find good embeddings from your data. For 120 years, people do principal components. You find hyperplanes that pass through data. For maybe 25 years now, so in the year 2000, there were two wonderful back-to-back papers in Science magazine. One was about local linear embedding, and the other was about isomap. And this is now nonlinear data mining. And what you see here is an example from diffusion maps, which is my particular way of doing data mining, since I work with Rafi Koifman, who developed this. You have low-dimensional data, two-dimensional, as you see, this ribbon on the left, that live in a 3D space. And you can construct an eigenproblem based on a fictitious diffusion between the data points that gives you a parametrization of the data. You see phi2 that comes out of data mining has to do with the length of the ribbon, and phi3 has to do with the width of the ribbon. Anyway, you do data mining in order to find good variables. So how did we work with the variables in this problem where we had a single time series? Oh, gee, we used autoencoders. So autoencoders, to the best of my knowledge, were proposed in 1991. You see the reference at the bottom by a guy whose name is Mark Kramer, who did his PhD in chemical engineering in Princeton, has done a number of interesting things. In 1991, he published this paper that he called Nonlinear Principal Components, and that we today call autoencoders. And eventually he did not get tenure at MIT. He had a very nice career, nevertheless. But it's very interesting that somebody who came up with this did not get tenure. And what we did is that we took windows of the time series, 40 long delays, if I remember correctly, and then we were able to figure out that these 40 long dimensional data points could be embedded in a three-dimensional nonlinear space. And then we had the three variables in terms of which we could represent the dynamics. Now, what about the equations? These were the variables. Where did the equations come from? So this is interesting, I hope. It was interesting in 1992. What we did is that we created recurrent residual neural networks. And the point is not so much that we came up with them. The point was that we realized that that is what the Runge-Kutta does. So think about it a little bit. On the left, you see a Runge-Kutta. So you evaluate the right-hand side once, and then you take the result, K1, and you multiply it by a fixed small number, which is the time step over 2. You add it to the initial condition, and you evaluate F again. And you do these things again and again and again. Now, if you look on the right, you see an architecture that has in it, you see there's 4 copies of a neural network. This is the same neural network. It's a multi-layer perceptron. It was a multi-layer perceptron in 1992. And then there is a superstructure network, which takes the initial condition, yn, on the right, passes it through the network, gets the result, k1, multiplies it with a fixed number, and then adds it again to the initial condition, passes it through the same neural network. You do this 4 times. So this architecture of a recurrent, obviously, because you go through the same function 4 times, and it's also a residual network. If you look at the Runge-Kutta, what you learn at the top is not yn plus 1 as a function of yn. You really learn the difference between yn plus 1 and yn, which is called the residual. So Runge and Kutta, whenever they did this, actually did exactly the same type of architecture based on Taylor series that the computer scientists have rediscovered, choose your word. And training such a network on discrete time data, yn and yn plus 1, gives you an equation, a right-hand side, which when Runge-Kutta integrated passes very close to the points that you observed experimentally. This is the residual network that was published by Microsoft in 2015. If I remember correctly, Kai-Ming He, who now is at MIT, was the first author. If you look at it, it looks like a forward Euler. You see, you take y0, but you don't learn y tau as a function of y0. you learn something which, when multiplied by tau and added to y0, gets y tau. I mean, okay, everybody can recognize this as a forward Euler. You're fitting the right-hand side of an equation whose forward Euler will pass from y tau. But it's interesting that this was not motivated by integration. It was motivated by the vanishing gradients if you have successive layers of neural networks and you never bring back y0 into play. And so I guess my point is that the numerical algorithms that we know and love already have in them certainly some of all the considerations that go into the famous neural network architectures that are being used today on the machine learning side. Also, and then you can laugh at this is me kind of, I don't know, sour grapes. You can say my paper with the recurrent Runge-Kutta resonance has, I don't know, 120 citations over these 30 years. And this thing has already more than 200,000 in the last 5 years. So you have to do the right thing and you have to do it at the right time, but you also have to do it for the right application. Copper electrode dissolution is not so important, but image processing is. And because we had now the right-hand side of the equation, we were able to do the bifurcation diagrams, which is what you kind of see on the bottom left. There is a steady state that has a Hopf bifurcation, the limit cycle branches, the period doublings, the attractors, the time series. There is something also else a little bit more esoteric in this that is that Steve can appreciate and dynamical systems people can, but not that many others. When somebody learns the time one map of a dynamical system, then something very weird happens, because the discrete time problem because it does not have the translational invariance in time, has completely different bifurcations qualitatively than the original continuous problem. So when the original problem has a limit cycle, the discrete problem has an invariant circle, which has frequency lockings and has all, for example, invariant circles do not period double. Invariant circles do not have turning points. So all the bifurcations of the dynamical system are lost qualitatively when you go from a continuum to a discrete representation. It's not that there are no resolutions to this, but what was done, as you see here 30-something years ago, was in a sense the right thing. Don't try to learn the time one map, but try to learn the right-hand side, whose integration passes from the time one map. And again, kind of, we also did a lot of other things back then. This is kind of a quick summary. If you look at, for example, at the architecture on the right, and you look at the top formula, you will recognize a Clark-Nicolson, the trapezoidal rule. So this is an implicit network. You cannot just evaluate it. You need to solve equations in order to evaluate the network. And this is, again, one of the points that numerical analysis has a lot of the theory and architectures that are coming up today in machine learning. This is something that I found out from a Chinese collaborator, Ai-Ching Zhu. There is something that's called, certainly everybody knows there exists backward error analysis. So look at the top. If you have a true dynamical system and you have the actual solution and the numerical solution, then the comparison between the true and the numerical solution is forward error analysis. But there also exists backward error analysis. The typical backward error analysis is you look at the top left, you have something that is called the modified differential equation. That's an equation whose true solution passes from the numerics of yours. And then what you see in modern identification using machine learning, if you want, is what is on the top right. There's something called an inverse modified differential equation. And this has the horrible rubric inverse backward error analysis, which sounds, I admit, weird. But anyway, as you see, what we learned is an equation whose Runge-Kutta, whose numerical simulation, passes from the true solution of UOD. So this is what is being done in these architectures that I am telling you, and it's interesting to consider the proximity of the true differential equation and the inverse modified differential equation is a qualitative measure of how good the numerical simulator is. Again, my main point, I understand I'm not doing justice to it, is that there is a lot in our numerical analysis that is being rediscovered and reused today. And we did other things back then. This was doing gray boxes. That is, if you know a lot of the physics, all the black terms in the equations, and you don't know only one of the terms, the red term, oh, then you hardwire in your neural network all the black terms and only learn the red term. We also did partial differential equations, so we got movies. What you see here is snapshots from carbon monoxide oxidation. So this is a clean platinum catalyst surface. What you see in every pixel is maybe 500 microns by 500 microns of the catalyst. It is viewed through a spectroscopy that's called photoemission electron microscopy. For those that know this is measuring the work function on the surface. That's the color that you see, and the color tells you what is absorbed on the surface. So red is more oxygen and blue is more carbon monoxide. And you see there is snapshots in a movie. You take the snapshots, you do principal components, you get the basis functions at the bottom left, and then you use neural networks here, delayed, so time delayed tokens embeddings and neural networks to learn in effect, to learn the solution of the partial differential equation. That is, you're finding the time series of a spectral representation of the solution with eigenfunctions on which you do the spectral expansion being the principal components that come from the data themselves. This is just to tell you that the predicted attractors and the true attractors, the experimental ones, were very close. This is doing approximate inertial forms using neural networks. This paper is in 2000, and this is a paper from 1994. This is closer again to turnstiles and to horseshoe global bifurcations for maps. This is with experimental data from Bob Ecke in Los Alamos. It comes from doing Rayleigh-Benard convection in the quasi-periodic regime in, God help me, superfluid helium, liquid helium at close to zero temperatures. What you see at the top left is some experimental Poincaré maps. You see kind of a two-looped torus. And what we did is that, again, we used, well, multi-layer perceptrons to learn these Poincaré maps and do the bifurcation diagram for the breakup of invariant circles in Rayleigh-Benard convection. Another thing from back then, and I think this is the last thing from back then I'm going to show you, is operator learning. So this is a paper from 1998, and it has to do with learning partial differential equations, i.e. learning operators, learning the right-hand side of partial differential equations from data. If you think of a parabolic PDE, to make it easier, you see that in a parabolic PDE, the time derivative is a function of the field, V, and a few spatial derivatives and some parameters. So if you have data, a movie from a partial differential equation, at every moment in space-time, you know from the data what is ddt, you know from the data what is ddx and d square u dx square, and therefore you can just use a multi-layer perceptron to learn not the solution of the PDE, which is what Fourier operator learning and what George Abak, my friend, is doing, which is using DeepNet. There, you learn the solution of the problem as a function of initial and boundary conditions. Here, you don't learn the solution, you learn the right-hand side of the differential equation, and then you can solve it whichever way you want. There is lots and lots of work along these lines the last 5 years, but this is something that was done back then. And it's interesting, again, to maybe show this, because if you look at the pictures from that paper, look at where it says finite differences in the picture on the bottom left. Let's say you take a 5-point stencil, ui minus 1, ui plus 1. Using finite differences, you estimate the spatial derivatives, and then using a black box neural network, here this was just a multi-layer perceptron, given the data, you learn the time derivative as a function of the space derivatives. And I'm showing this again because at one location in space, you have this, and then if you shift to the next stencil to the right to you, the other 5 points, then that also provides you data to learn the same function. And you shift the stencil, shift the stencil, shift the stencil. And basically what I'm trying to tell you is that finite differences are convolutional neural networks, a particular kind of convolutional neural networks. And so what we did back then is that we combined convolutional neural networks in space, what you see at the top right, and recurrent neural networks in time at the same time, which is the Runge-Kutta stuff that I told you. And we learned equations. We learned the right-hand side of equations, not their solution operators, the right-hand side operator based on data. And now what I'm going to do, and the same idea in stochastic differential equations. Again, the idea is to train your neural network, create an architecture that is based on what the numerical analysis algorithm for solving SDs would be. So you can create neural networks that are based on Euler-Maruyama or on Milstein or on Freund, and we have also some work in more recent years these days. All the numerical analysis goes into the loss function. You organize the loss function by assuming that the data come from an Euler-Maruyama scheme of something, a Milstein scheme of something, a Freund scheme of something. So the basic idea again and again, sorry, this is the last time I think I'm saying it, is numerical analysis as we know it contains in it a lot, if not all, the architectures that computer scientists come up with, and in particular, maybe this is like recent, the paper on the right, as you see, is May 2024. The paper on the left is a very nice paper. It's end of 2021 by Nick Zabaras and one of his students, collaborators. And basically the idea is that transformers are also integrators. What the paper on the left says is that the expressivity of transformers, the prediction part of them, is expressive enough to look like multi-step linear integrators, like Adams-Bashforth and Runge-Kuttas and whatever. Adams-Bashforth schemes. And then the paper on the right, which is like, last month, says, oh, gee, if I take a transformer to learn a linear system, the prediction part of the transformer looks like the exponentiation method for solving a differential equation. So again, my point of view, what you see is something else that's very celebrated and part of most of the LLMs. At heart is an integration in the right latent space. A last thing that I wanted to say, and this has to do a little bit with my short visit at DARPA, a couple of years, my first program that I made is kind of contained in this picture. If you look on the left, remember that I told you there is learning the function whose Runge-Kutta passes from the data. So what you learn is the red part. The black part is the Runge-Kutta structure. It is given by Runge and Kutta, by numerical analysis. So if you have data and you know the algorithm, you can learn the function. That is the red part. Contrary, if you have data and you have the function, then you can learn the integrator. So the idea is that one can learn algorithms from data by doing optimization or by doing neural integration search. And the first program that I did at DARPA had to do with exactly like here. Here you see using optimization to find neural network architecture, something called meta-learning. My first program is using optimization to find numerical algorithms, new numerical algorithms. And I kind of like this duality that the same philosophy can either be used to learn the problem if you know the solution, or to get the solution algorithm if you know the problems and the solutions. So this comes under what these days is fashionably called in-context learning. And this is something different. I think I have time to tell you two little different things. In general, we talk about the reduction for dynamical systems, and we mean reduction of the number of variables. But it's interesting also to think, how would we do parameter reduction if we have a problem that depends on 10 parameters, but it really depends, a problem that depends on the Reynolds number, and the Reynolds number is a function of 5 other things, a nonlinear function of 5 other things. How do we figure out which combination of the parameter matters and which combination of the parameter does not matter in a data-driven way? There is nice tools for, there is active subspaces by Paul Constantin that has to do with dimensionless parameter. This is a sort of dimensionless, data-driven dimensional analysis. If you talk about only products and ratios of parameters, there is some nice work of Paul Constantin about active subspaces. Also, there is work on by by Sethna at Cornell about what they call sloppiness. Maybe this is an example of sloppiness. Look on the left, you have a problem that there's two parameters, P1 and P2. But what really matters is the product, P1 times P2. So this means that there are whole level sets in which the parameters are changing on the level sets, but the answer remains the same. So the idea is, how can we do this? You see the same picture on the right. How can we, in a data-driven way, figure out which are the directions in parameter space in which the quantities of interest change, and what are the directions in which the parameters don't, the response does not change. And so we want to discover the meaningful parameter combinations, test their interpretability. We can build data-driven models with these parameters, and in effect, we want to disentangle the redundant parameter combinations, redundant for prediction of the output, from the meaningful ones, the ones that affect the prediction of the output. This is a very quick example. This can be done in several ways, but this is something that we call Y-shaped conformal autoencoders. And it's a very simple thing, which I will try to explain, but this is something that is relatively recent. This was published a year or so ago. So I'd like you to think of a very simple system. Look at the top left. It's a small enzyme kinetics problem. And you see there is three parameters, Kf, Kr, and Kcut. And you will take my word that in a certain regime in parameter space, it's true that there are three parameters, but there exists a single effective parameter, which, if you know the equations and you do it by paper and pencil, it's Kf times Kcut over Kr plus Kcut. But you don't know this. You only have the responses. So what you do in order to figure out the effective parameter in a data-driven way is to, as you see at the bottom left, take an initial condition and then take all short responses that come from all perturbations of the parameters. So you really perturb, in a little cube in parameter space, and you get the response of the system. Now, there are three things that we are varying, but since, as I told you, one thing matters, if you do data mining in all of these responses, you will find that they are a one-parameter family of responses. So this already suggests that only one combination of the three parameters matter. And now we go to the Y-shaped autoencoder in the middle, which looks a little bit weird, but basically you take the three parameters, that's the blue at the input layer, and then you don't try to reduce them. What you do is that you create a latent space in which one of the parameters can be fitted to the output. So this is the first green neuron that goes and fits the red outputs. And then the other two neurons in the middle layer, they are supposed to be enough so that they can reproduce the three parameters, Kr, Kf, and Kcut. So the idea is that you take the three parameter space and create a parametrization of the three parameter space that is the product of one direction that pertains to the output and then two directions that do not change it at all. So the most important thing is the bottom line in this slide, and that is the extra thing that makes this architecture work. You're asking for the first green neuron to be orthogonal in latent space to the other two. That is, you're trying to decompose the solution into a product of two manifolds, one that matters for the output and one that does not. There is also ways of doing this spectrally, much more, I don't know, I'd say more dignified if you want, but this is a particular way of trying to disentangle the combination of parameters that matters to the output from the combinations of parameters that do not matter. And I will also skip this. In the last 5 minutes, I'd like to talk to you about something that I am particularly fond of. It's relatively recent, maybe I think the paper was published a couple of years ago, but we're actively working on it, and it has to do with the idea of emergent space and emergent time. This is a very nice paper by two people that they published it in Science magazine in 2013. It has the very nice title, the latent geometry of contagion. What they did, I think to understand it, you look at the bottom strip. You can see, you can recognize the Earth, and then the red dots are cases of the first SARS virus, the avian flu, as it was developing around, I think, 2011, something like that. And you see that as time goes on, you get more and more dots around the Earth. But then what these guys did is that they took, and that's on the top left, they bought all the records of all the international flights at the time. There is a company that sells them. We tried to buy them also just to reproduce this, and they wanted something like $8,000 or $10,000, so we didn't buy them. But anyway, they got those, and then they constructed, based on these data, the picture on the bottom left. On the bottom left, you see the Earth, but scrunched. The Earth is deformed in such a way that cities with equal frequency in communication are at equal distance. And if you do this, it's kind of lucky that it happens in 2 dimensions, but if you do this, then in this deformed Earth, as you see at the middle kind of row, the evolution of the contagion looks very much like a concentric growing circle. So the idea is very much an idea like what we do in normal forms in dynamical systems. Find the transformation of the problem in which the evolution is nice. What is nice in normal forms? You have the smallest number of terms. Here, you look like a very nice concentric circle. But the idea is transform the problem in the same way that by using logarithms, we transform the problem so that something is easier, like multiplication becomes addition. Here, you transform the problem so that the evolution of the virus is a much easier problem to solve in the deformed space. So you go to the deformed space, solve there, and bring the solution back, just like with logarithms. And this is something that I like. Look at the first line. It says, since we cannot change reality, let us change the eyes with which we see reality. That's from Nikos Kazantzakis, who is a Greek author of the middle 20th century. This is kind of an attempt to joke about this. On the left, you see Dora Maar, who was one of Picasso's muses, as painted by Picasso. And then in the middle, you see her as photographed by Man Ray. And it's the same person, but everybody sees the same thing in different ways. So the thing that I want to tell you in now 3 minutes is that in 2011, DARPA had something that was called the Shredder Challenge. They took 5 documents, they shredded them, put the shreds on the web, and asked people to put them back together. They gave $50,000 to whoever put them back together. And I think 2 months later, a company in San Francisco did this. Our grad students can do it in, I don't know, half an hour now. And even we could do it if we still program. What's the basic idea? It's the same as puzzles. If you take a picture and you shred it in pieces of puzzles, then you put it together based on what? Based on smoothness. So here is a partial differential equation on the left. It's a Ginzburg-Landau in space, x, and time, t. You see the patterns that come from the solver of the equation. You take this equation and shred it in 512 time series, and then you shuffle the time series. So you don't know at what point the time series happened in space. But if you analyzed each of these time series as each time series as a data point, and you look at the similarity between the data points, that is smoothness, and then you find that it's a one-dimensional family of time series. And if you order them based on the first diffusion map or the first principal component or whatever, then you get space back. Actually, you get a flip of the space, because reconstruction based on similarity cannot understand if you're looking at the picture on the right or on the left. The idea being that data mining can recover the important underlying geometry if it has been shredded or masked. And so this is the last thing I want to show you. It's 800 different oscillators. It comes from the work of Strogatz in the late 80s. If you run these oscillators, they are both phase and amplitude. So both X and Y depend. The dynamics don't depend just on the angle, but depend on the angle and the amplitude. And if you run them, you will see that they very quickly all organize themselves along a curve. And then they keep on doing things, but they keep this organization along the curve, which very strongly suggests that if you would like to model them, the right space is not X and Y, but rather things that happen along the arc length of this curve. And if you plot the behavior as a function of the arc length on this curve, the radius and the angle as a function of the radius of the arc length of the curve, then as you see on the right, it kind of looks like partial differential equations. So what we did is that we took these oscillators and then we took their behavior and then we analyzed their behavior and then ordered them based on their behavior, not based on where they were, but based on what they do. So their behavior looks like a mess of spaghetti, but if you relabel the oscillators, you put the right oscillator next to the right oscillator. Who is the right oscillator? The one whose behavior is close to yours. Then, in this space of behaviors that you see described by phi1 on the right, the behavior of the oscillators looks like a very smooth field. And in this smooth field, instead of looking at the individual oscillators, we can learn a partial differential equation, not in physical space x, but in this emergent space. In a dimension, you were used to finding latent spaces for the dependent variables. This is finding the right latent space for the independent variables. Rearrange the problem so that in this new space, which is parameterized by phi, the behavior is nice. And by doing this, we can learn the partial differential equation. What you see here is a bifurcation diagram of this partial differential equation. You see that as you change the strength of the coupling between the oscillators, you go from uniform space-time solutions to periodic space-time solutions. And maybe the last thing that I'm going to say here is that if you have found the partial differential equation as a black box through operator learning, then what are the right boundary conditions? It's not clear. For most, what makes a well-posed problem? For most problems that we write down analytically, we know how to check what constitutes a well-posed problem or not. We look at the nature of the equation. Is it parabolic? Is it hyperbolic? We look at the initial and boundary conditions available. We have ways, if you want, of testing problem well-posedness. For a black box operator, what makes a well-posed problem? I don't have time to talk about that. I had another little talk about that, but there are papers on it. Maybe what I would do now is kind of get out of this and go back to the beginning, to the second page. And well, let me go up there and put up the picture and then say that Steve and his work and his books and his students, with many of whom I still work, have been a big resource for almost all of the work that my group and me and my students and collaborators have done over the years. And in particular, this issue of the qualitative nature of the bifurcations of discrete versus continuous systems is something that we still talk about on the phone. So let's say 23 years since 1991. Steve, I don't know where we will be in what will it be, 47 or something like that. But if we are around, let's get together again and have tapas in Madrid if possible. Thank you all. I'm sorry I missed being there. I'm glad I at least was able to show up electronically. Thank you.
Thank you so much.
Well, I guess I should say that his hair is a little more white than red as it used to be at the time.
Thank you so much. Very nice talk. Are there any questions or comment?
Well, Steve should say something.
I want to say something. In one of the slides, you make a comparison between learning model or learning algorithmic.
Yeah.
What you think that is the way to approach from the data? Because now we have a lot of data, so what is the best way to try to solve this type of problem? For instance, in climate.
Oh, God help me. Climate is a difficult problem by itself. I have enough trouble doing this in very well-controlled problems. I like to stay there. However, as you know, there is many people in the world. I mean, for example, Paris Perdikaris, who was a student of George Karnadakis and is now at Penn, and he spent the year at Microsoft in Holland, in Amsterdam, I think. I mean, among the many people that did this is the most recent interesting paper that I know, where people learn the operators from data. I admire and applaud and read some of the papers of the people that do this. What somehow either I like more or is the place where I think I can contribute something, is rather to work on control problems and try to understand I don't know how to say it, the details of what they're doing in controlled environments. So I don't so much work on, I guess, real big problems where what matters is the result. I rather am interested in the interplay of the numerical analysis with the techniques that people like that use. But so I don't work there. I admire those that work there. I am happy that somebody else that is so good like they are do it, but that is too messy a problem for me. I'm glad they are doing.
Another question from the room, and you talked about how, what is old is new again. We can find in numerical and the classical numerical methods, the architectures of these methods that are being sort of reinvented by computer scientists today. But one notorious thing about the neural networks type of methods that are popular now is that they lack the sort of deep theoretical analysis that we have in numerical methods, where we can make statements about convergence with respect to parameters of discretization and so on. So does the parallels that you're making in this talk potentially give us some way to look at those gaps in theoretical analysis that could help with statements about the behavior of those methods?
Yeah. So I have a couple of very cheap answers. I think the basic thing is yes, but I'm going to have two very little examples. It is very easy to see that if you learn the time one map of something through a neural network, what you learn will in general be non-invertible. That is, if you have something and you have a neural network xn plus 1, generically, if from xn plus 1 you try to go to xn, then there will be many routes. Why am I telling you this? Because if you have differential equations, then the trajectory should be unique backward unless something happens. So this is a generic neural network is an architecture that has pathologies that are based on, for example, non-invertibility. So people realized this and they created invertible neural network architectures. This is just a small example. It doesn't answer, but yes, there is ways at which numeric analysis goes back to feed into neural network architectures. And there are people, I think, just one person I know that I actually even work with, Sid Mishra at the ETH is a numerical analyst who looks at the accuracy of some of these solution methods. After all, what is pins? My physically informed neural networks is, I hope everybody will forgive me for the quick analogy, it's collocation on neural network basis functions as opposed to doing it on Chebyshevs or something like that. So yes, there is a lot of numerical analysis, and yes, I think it would be helpful. But the other cheap answer I wanted to say is, anecdotally, I had a discussion about exactly what you said with Vladimir Rokhlin sometime this year. And he said, the computer scientists are very smart people. Instead of trying to tell them what to do, maybe we should do fast algorithms for what they are doing, which I think is, again, a nice quip to say. The quick answer for what you said is yes. But anyway, I think it's a very fruitful direction. I also very much like, the typical joke, you will forgive me, I am old now and I can say things like that. When I first saw things like resonance and so on and so forth, the typical jokes is, said the old professor, all of this is wrong, and I published it first anyway.
Any other question, comment? Okay, well,
Yeah, Steve will say something.
Yeah, I couldn't resist. I have a question that I would hate to be asked myself, but I'm going to ask you anyway. It's been an interesting day because Daryl started out this morning and you ended up the day, and you and I and Daryl have have a shared past in many ways and shared life through Los Alamos and other things. But yeah, this is a bit hard to express, but I think maybe you can kind of figure out what I'm trying to get at.
Go for it.
Okay, so, well, it wasn't 1984, it was 85, it was 84. We met in Phil Holmes' office. Your thesis advisor, I think it was Eris, came to Cornell to talk to Phil about the problems you were working on. I think it was phase locking and circle maps, something like that.
Yes.
And another student in chemical engineering. So you started out in your PhD is in chemical engineering, which is interesting. You ended up very differently. The trajectory of your career, and that's something I've been thinking a bit about here, is the trajectory of careers over time. You never know where they're going. But so the things you worked on in, say, your PhD thesis and until you got tenure at Princeton, on the surface are very different than the things you're working on today. On the other hand, the basic one of the things that came out of your talk is the basic techniques and ideas were really being germinated in all your work from early on. And nowadays we have these ideas of machine learning, neural networks, AI, and so on, which is, if you look at it on the surface, it's very hard to penetrate for many students and for people in general. But the general principles are, as you talked about, are based on a lot of fundamental ideas that are taught, that have been taught for quite a bit of time in graduate school, applied math, and so on. Do you have any comments about? And the final comment you made about the old guy saying that's wrong, and I published that many years ago. Do you have any comments about how the way the ups and downs and waves of science and where we are now versus where we came from and where we're going? That's a good question for a DARPA program director.
Oh, I'm going to answer it in this case not as a DARPA program director, but as a professor. When I started, I got I got several teaching awards from the students, from the university, and so on and so forth. I thought of myself as being a good teacher. And then in recent years, my evaluation are not things to be very proud of. And I don't think it's because I don't care, nor do I think it's because I don't put effort, nor anything else. So I think that the main thing that has changed is the way that the kids, if I may call them like that, are learning today. And I am not very cognizant. Nobody has ever taught me, and maybe I should put some effort to be taught about the way that they're learning today. You know what I mean? There is like a quantum of the 15-minute talk, and is there a solution close to mine? For that matter, it very much looks as if what most of the LLMs are these days is I look among all the solutions in my pocket and find which is close to the question that I'm asking now. I very much wish, so my answer to what you're saying, I very much wish somebody who is knowledgeable would teach me how to teach the kids today. I don't know how to teach the kids today. You and I learned in a different way in which we blocked off the world for 2 hours at a time or whatever and took a book. I mean, I know you said when you started at Caltech, this is a memory from a long time ago. For what did you say? 2 years you didn't go to any conference, but you sat in your office and worked or something like that. People don't learn this way these days, and that is not their fault. This is the way that the tools that we have are. And I wish I understood it better. I hope maybe I still can understand it better. So I didn't answer, but people learn differently these days than back then.
Hi, Yannis. It's Duan.
Hi, Duan. How are you?
Good. Good to see you here.
Good to see you.
Some years ago, in a casual conversation with you, or maybe in a dining table, You mentioned that you realized that developmental biology was a good topic to work on by mathematicians or applied mathematicians like us. But for some reason, you did not get into it. It sounded like that you regretted a little bit or something like that. So my question is, in the time of data science, AI, machine learning as it is today, do you think, or what's your perspective on interface of applied math, data science with biophysical science?
Okay, that is a huge thing, and people work
one
there.
aspect is fine.
Here is So just because you talked about developmental biology, so it turns out that I had a very good student who Stas Schwarzman, who saw the light and became an experimentalist after working with me, and then became a professor in genomics in Princeton, and also now has a lab at the Flatiron Institute with the Simons Foundation, who does developmental biology a lot from the experimental side, but is using a lot of the tools that we are using now. As Steve maybe was saying before, many of the choices of what we do is a little bit serendipity. I mean, who do you happen to have near you that has an interesting problem? So I have done a little bit of work in this. The one thing that I'm going to say that is maybe useful is that what is quite impressive these days is that in olden days, people had 3 things that they could measure every hour. And now you can look at every cell in the embryo and get, 50 time series of messenger molecules, and have space and time and resolution and so on and so forth. So things that have to do with data fusion, what is common between different data streams. There is simple things that I can still relate to that excite me, but the confluence of this huge set of data streams makes things both exciting and scary and much more rich than, if I may say, you and I, the type of time series. Like, look, I gave you a talk even now today for having one time series of one thing, and now people have 500,000 time and image series, and they have to orchestrate them together. That's a very exciting subject for all of us. I think I didn't tell you any real answer besides saying that there is so many exciting questions, in some of which we can still have, hopefully, a contribution.
Thank you.
Sorry, like, for example, in what I told you about briefly about the parameter values, you have many things, but some combination of these 10 things affects what is happening, and the other combinations don't affect it. Just this by itself is, if you have several streams of information, what is common between these streams? Maybe the other thing that I had in my abstract and I didn't get to talk about, and I will really shut up after that, is if you're going to learn a function, you have first to learn what is x and what is y, like which thing is a function of which. Then you can go on and, use Gaussian processes or neural networks or polynomials or differential equations to learn a function. This subject of figuring out, of course, this is canonical correlation analysis, but at the same time, there is very exciting techniques today on trying to figure out what is common between different streams. If you have somebody looked by 2 instruments, what of the state of the instrument pertains to the diseased person, and what of the state of the instrument is the electronic noise of that particular instrument. So there is lots of, I'm just saying, you just have to look, I'm saying a platitude. There's lots of very interesting things, and we can even be useful in some of them. Thanks.
Well, thank you so much. Very nice discussion. I don't know if anyone want to say something. Other question? So, well, let's send the speaker again. Thank you so much.
Thank you. Health and happiness, Steve. And talk to you. Bye. Thanks, Macrina.
Bye. Well, this is the last talk of the day, the last talk of the conference, so I am sure that Anna wants to say something. So
thank you very much, everyone, for participating in this very nice meeting and very interesting. So what I want to say is that I hope you have learned a lot, you have enjoyed a lot, and I also hope, Steve, that you have enjoyed a lot and have fun and have enjoyed between friends and among friends, and that's it. I think you wanted also to add something to WordPop.
Thanks, Anna. Okay, so the last few years, I've been teaching the last teaching block of the day, and everyone's tired. Nobody wants to be there. Everyone wants to go home or go do what they are going to do for the rest of the day. But one of the things I always do then is I start off my class by saying, okay, does anybody have any questions? No questions. Okay, that's usually the response I get. And then I go to people individually and pick them up and say, you're going to have to ask me something today. I'm not going to do that today, but this has been very special for me in a way that I really didn't think it would be, or didn't know how it would be when the meeting started. So I'm very grateful for Anna, Macrina, Hezebel, Manolo, Victor, and Reza for organizing this. I know these things take an awful lot of time out of their busy schedules, and I'm really grateful you've done this for me. And anyway, so it's been great working with everyone here, all of those people that I just mentioned. And it's been an interesting career so far. I sort of read a lot of things that Giannis talked about. Really struck a chord with me, the idea of not knowing how to teach anymore, and students are learning in different ways. That really visually came home to me when I was writing a book I was teaching a course on classical mechanics and writing a book on it at the same time. And I got at the end of the year, I thought I did a great job, and that was going to be a perfect book. And even if they didn't like my lectures, they could learn everything from it. And at the end of the year, you get these nice student evaluation forms, which we all know and love. The younger people have, if they haven't gotten them yet, they have something to really look forward to. And one of the comments by one of the students was, his notes are too long. And that really annoyed me, because I put so much effort in that to write everything I knew about, angular momentum or torque or Newton's 3 laws. But then after thinking about it, I realized that they had a point, and that students were exposed to things differently. I didn't grow up with the internet. Can you imagine that? But they process information in very different ways, and I needed to adapt. And probably the best experience has been to get me to adapt quickly is teaching at the Naval Academy the last couple of years. And I've learned a lot about teaching there. You never stop learning, no matter how good you think, how much good you think you are, how much you think you know. So those students have very limited time. They're very capable. They're as smart as any student anywhere, but they don't have the time. So you got to deliver the same amount of information to them, and they have to absorb it in a much less amount of time. So when I went to in the old days, when I was taught, your professor gave you a huge homework assignment that you would spend hours on every day, and maybe you could get it done in a week. Well, that's just not practical. I would get horrible student evaluations if I did that at the Naval Academy, but it's not necessary. And so, you know, if they spend more than 3 hours on my homework assignment, I've failed in getting the information across, and that's one of the things I've learned, how to get information across to students. So teaching has become much more rewarding for me in recent years. Research is, you know, I love doing research, but teaching is a lot of fun. And my research and teaching have gone hand in hand forever, and I never stop learning, no matter what I'm teaching. Calculus, I learn something new about calculus every time, classical mechanics, and so on. The other thing I want to mention, sort of for the younger people, and it's nice that so many were brought by their supervisor, that, you know, you guys don't know how good a supervisor you have to bring you to meetings like this, because it's very important. I always try to bring students to meetings if possible, but they often don't have time for such a thing. But careers don't work out the way you think they are going to. And somebody said, I wish I said it, but I'm not, life happens when your plans don't work out. And that's pretty much the way things worked out for me. And, you know, everyone said nice things about me here, mostly, the things I heard. So, you know, I did my PhD, and up to that point, you know, I had many starts and stops, and things I thought I was going to do with my career I didn't do. I wanted to be an engineer after I got out of high school. I wanted to be a physicist after my undergraduate. I ended up doing nonlinear dynamics. And that was the best decision I ever made. Did I do that consciously? No, I just thought the subject was interesting, and there was a future to it, and it was starting out, and I wanted to be part of something that was starting out. And so I was lucky in that way. So I had a great supervisor, Philip Holmes at Cornell. I did my thesis. I didn't realize that thesis was setting me up for nice things, and I've used that thesis off and on ever since I turned it in 1985. And then I applied for jobs. I applied for jobs to about 80 or 90 places, like people do, and I got rejected from every last one of them. And I thought, God, I'm going to be a failure. What am I going to do with my life? Maybe I'll have to, I don't know. So at the last minute, so this is May, and you know, if you're applying for jobs in May, you're in deep trouble. So this one place, a respectable state university that I won't name, invited me for an interview. They were, you know, all their people had turned them down. I interviewed, and they offered me a job, and I thought, if I accept this, this is an okay place. The people here are not great. They're not working on interesting things. If I accept this, it's the only job offer I had, my career is going to be over. So I turned it down, and I wouldn't consider myself an overly brave person, but I wasn't sure what I was going to do. But I knew I didn't want to get stuck in a dead-end job with people that I didn't think were great. So, in terms of research, so it's important to work with good people and to have good problems. I got lucky. I found a temporary job at Caltech because somebody turned their position down, and that someone was coming through giving a seminar, and they were desperate. My supervisor said, oh, you should look at this guy. He can probably teach your courses you're interested in. And that worked out to me staying there for 15 years, which was okay. But what Yana said also is I broke every rule about being a young academic, and it worked out okay for me. I didn't network and go to conferences. I sat alone and worked. I sat in the library and read. I would sit in the stacks. I mean, I haven't been to a library in 20 some odd years now. These were the old days when that's how you processed information. That's one of the things I had to learn. People don't do that anymore. I just sat and worked and learned about things, and because I wasn't ready to really contribute anything. And then I started thinking about things. My first book, I wrote that when only 3 years out of my PhD. That was a dumb thing to do, many people told me. But I had a few good people say, you know, that might not be a bad idea. This is an up-and-coming area, and there are not a lot of books. So I wrote this, and it was a good thing to get some of my work published, because my first 3 papers after my PhD were all rejected, and that was also a big ego blow. But to go on and go on, so there a lot of disappointment, a lot of breaking the rules, but it worked out okay for me in the end. So that's the thing I would advise young people to do, is to follow your own inclinations. I mean, you can take advice from other people, you can evaluate it yourself. There are no hard and fast rules. Things change all the time. What's going to be going on in the future, which is kind of related to the question I was asking Giannis, is not what's going on now. It is true that us older people are going to look down and say, you know, this machine learning and stuff is, you know, we did it all before and it's not going to amount to much. But that's not true. It's going to change the way every bit that we do science, and you should embrace that. Just like when people came out with computers in the 80s and people said, oh no, you know, that's going to ruin the way we do mathematics and you're not going to be able to think properly and so on, and that was all turned out to be nonsense. Anyway, that's enough of me going on about this. I want to thank everybody again for coming. Thank all the organizers. This has really meant a lot to me, and I'm grateful to all of you. And if anyone wants to send me email or ask me questions, please feel free to do that. And everyone who's going back, please have a safe trip. And hopefully our paths will cross at another meeting in Spain. Because, as you know, Spanish meetings are special. Everyone talked about the 1993 Sagaro meeting. Everyone who's ever been to that meeting will say that was one of the highlights of their professional lives. Now, it's normal to kind of say that and be complimentary, especially if you're in Spain, but it really is true. You know, you get to have dinner with Arnold and Moser. I met a huge number of people there. There was a Greek mafia. I was met when I got off the bus by Yanis Simenis. I didn't realize I had met Harris there. A huge number of people that I've intersected with my entire career. So I'm contradicting myself, aren't I? I said, don't go to a lot of meetings. Stay there. And I didn't, but I looked at the list of speakers. This wasn't some giant meeting with 500, 800. This was a very intense 2-week meeting where you got to sit down, eat and drink and hike and go on excursions with people in your area and learn new things, and it was a very special time. I don't know why I got off onto that, but anyone who talks about Sagaro can't help but do that. It was quite a nice meeting. Anyway, thank you very much. I hope we meet again in the future, sincerely, and thank you again very much.
Thank you, Steve. Thank you. So we are ready to go then. Have a safe trip back and enjoy Spain and the summer. Okay.